Hello, and welcome back to the Sleepy Professor, your sanctuary for slowing down, unwinding, and drifting into the embrace of scientific wonder. Tonight, we're embarking on an extraordinary voyage, one that will carry us across an almost unimaginable span of time, 160 million years. We're traveling back to an era when colossal creatures walked the earth, when the ground trembled beneath footsteps that could crush stone, and when the skies belonged to winged reptiles that dwarfed any bird alive today. Before we begin our journey, I'd love to connect with you. Where in the world are you watching from tonight? Are you nestled in bed as city lights flicker outside your window? Or perhaps you're somewhere quiet, where stars still pierce the darkness? If you're discovering this channel for the first time, I'd be honored if you'd give this video a like and join our community by subscribing. And to those who've already become part of our family here, thank you. Your presence means everything. Don't forget to tap that notification bell so you won't miss our next adventure into the wonders of science and history. Now, a gentle promise before we dive in. This video is crafted specifically to help you relax and ease into restfulness. My hope isn't that it keeps you wide awake with excitement, though if it does, at least you'll drift off a little wiser and filled with wonder. So go ahead, settle deeply into your pillows, let your shoulders drop, feel your breathing slow and deepen, and allow your imagination to open like a portal. Picture, if you will, an ancient world stirring to life around you. What was it truly like to exist in the shadow of dinosaurs? What did the air smell like? What sounds filled the prehistoric dawn? When the world nearly ended, our story begins not with triumph, but with catastrophe. Rewind your mental clock to 252 million years ago, a time so distant that even the continents themselves would be unrecognizable to modern eyes. The Earth had just staggered through the most devastating mass extinction event in the entire history of complex life. Scientists call it the Permian extinction, though it has earned a far more chilling nickname: the Great Dying. Imagine a world gasping for breath. More than 90% of all marine species simply vanished. The oceans, once teeming with bizarre and beautiful life forms, became graveyards. On land, ancient forests withered and collapsed into ash. Animal populations plummeted so dramatically that the fossil record shows vast stretches of time where life itself seemed to hang by the thinnest of threads. It was as close as Earth has ever come to becoming a dead planet. But life, stubborn, resilient, endlessly creative life, refused to surrender entirely. What followed was a long, fragile recovery, a slow rebuilding from the ashes, and into that vast vacuum of ecological opportunity, into those empty niches left by vanished species, stepped the earliest ancestors of a group that would reshape the planet, the dinosaurs. A world transformed, the Triassic dawn. The Earth of the Triassic period was a world in profound transition, barely recognizable to anyone accustomed to our modern planet. All of the continents, every single landmass, were fused together into one colossal supercontinent. Scientists call it Pangaea, which appropriately means all Earth. Imagine it stretching from pole to pole like an immense, cracked, sun-baked puzzle piece, surrounded by a single planetary ocean. The interior of Pangaea, far removed from the moderating influence of the sea, endured a climate of brutal extremes. Days could be scorchingly hot, with temperatures that would make modern deserts seem comfortable. Nights plunged into bone-chilling cold. Much of the land was arid, bone-dry for months on end. Seasons didn't flow gently from one to another. Instead, they could swing violently from blistering droughts that turned the earth to cracked stone, to sudden explosive bursts of rain that transformed dry valleys into raging torrents overnight. The landscapes themselves reflected this harshness. Vast stretches of red deserts where dust devils danced in the scorching afternoon heat, sprawling floodplains that could shift from parched wasteland to muddy marsh in a single storm, and river valleys where water was both precious and dangerous. This was not yet the lush, fern-draped kingdom of giants that would come later. Rather, it was a testing ground, a crucible where new forms of life experimented endlessly with survival, where evolution tried out countless designs to see what worked and what didn't. Among the survivors of the Great Dying were archosaurs, a remarkable group of reptiles whose destiny would fork into two of the most successful lineages Earth has ever known. One branch would eventually lead to crocodiles and their relatives, creatures that would perfect an ambush predator lifestyle so effectively that they've barely changed in millions of years. The other branch would lead to dinosaurs, and through them, to the birds that fill our skies today. The first dinosaurs, humble beginnings. If you're picturing the early dinosaurs as towering, earth-shaking titans, I'm afraid you'll need to dramatically scale down your mental image. These pioneers were not the colossal creatures of later eras. Instead, they were small, light-footed, and remarkably quick, more like shadows flickering across the landscape than lumbering giants. They darted through sparse undergrowth and across open ground with nervous energy, always alert, always moving, living cautiously beneath the relentless Triassic sun. Consider Eoraptor, one of the earliest known dinosaurs. This creature was scarcely bigger than a medium-sized dog, with long, graceful legs and sharp teeth perfectly suited for catching small prey, lizards, early mammals, large insects. Another early pioneer, Herosaurus, was somewhat more imposing, yet still modest when compared to its future descendants. It stood perhaps 2 to 3 meters in length, moving with a nimble, almost cat-like gait that spoke of agility rather than power. But here's the crucial detail. These early dinosaurs were not alone in their world, not even close to being the dominant players. They shared their harsh Triassic landscapes with a formidable host of competitors, especially a group called the Pseudosuchians, the ancestors and cousins of modern crocodiles. And in the Triassic, the Pseudosuchians had the upper hand. Pseudocians came in an astounding variety of shapes and sizes. Some resembled armored tanks, their bodies encased in bony plates that could deflect almost any attack. Others were swift, two-legged predators that could sprint across open ground with terrifying speed. For the vast majority of the Triassic period, these crocodile relatives seemed destined to inherit the Earth. They dominated ecosystems from pole to pole, keeping the early dinosaurs in supporting roles, bit players in an evolutionary drama where they seemed unlikely to ever take center stage. It wasn't yet clear which group would ultimately claim dominion over the planet's open spaces. The future was unwritten, and from the perspective of a time traveler standing in a Triassic landscape, betting on the small, unassuming dinosaurs would have seemed like a long shot at best. The dinosaur advantage, standing tall. So what separated these early dinosaurs from their competitors? What hidden advantage would eventually allow them to outlast and outcompete the armored titans and swift predators of the Pseudocian world? The answer lies in something deceptively simple: posture. Unlike most reptiles, whose legs sprawled out to the sides in that characteristic lizard stance, dinosaurs evolved something revolutionary: an upright stance with their limbs tucked directly beneath their bodies, supporting their weight from directly below. This new skeletal architecture wasn't just a minor adjustment, it was a game changer. It allowed for far more efficient movement, consuming less energy with every step. It provided better support for body weight, opening the door to larger sizes without the mechanical problems that plagued sprawling reptiles. And perhaps most immediately useful in the competitive Triassic world, it granted advantages in stamina and speed, helping them chase down elusive prey or escape from larger dangers that couldn't match their endurance. At first, this upright posture was simply a survival tool, an edge in the daily struggle for food and safety. But later, much later, it would become the foundation for something truly extraordinary. It would allow some of their descendants to grow into the largest land animals the planet has ever seen, creatures so massive they seemed to defy the very laws of physics. But in these early Triassic days, the dinosaurs were still in their experimental phase, still tinkering with form and lifestyle. Some hunted insects and small vertebrates, darting among the gnarled roots of primitive forests. Others began tentatively nipping at plants, conducting the first experiments in herbivory that would later produce those colossal, long-necked browsers. They were evolutionary opportunists, quickly filling niches left devastatingly vacant after the Permian collapse. In an ecosystem still scarred and simplified by mass extinction, the winners weren't necessarily the biggest or the most powerful. The winners were small, adaptable survivors, creatures that could make do with whatever resources were available, that could pivot quickly when conditions changed. A Triassic moment. Close your eyes for a moment and imagine standing on the Triassic plains. The landscape shimmers under a haze of oppressive heat. Sparse, tough vegetation clings stubbornly to the parched, rust-colored ground. Red rocks glow like embers in the intense afternoon light, and the air itself seems to ripple and distort. Suddenly, out of the scrub vegetation darts a small, lithe, two-legged reptile. It pauses for just a heartbeat, just long enough to snap up an unwary lizard with lightning precision, before vanishing back into the shifting shadows cast by stunted trees. Its movements are economical, efficient, almost bird-like in their quick precision, though birds themselves are still an unimaginable 150 million years in the future. For now, these tiny hunters and cautious foragers are just another thread in the recovering tapestry of life, one group among many trying to make their way in a challenging world. And yet, in hindsight, with the benefit of looking backward across deep time, they are something far more significant. They are the seeds. The beginning. The first chapter of something extraordinary. From these genuinely modest beginnings will eventually come the sauropods, with their impossibly long necks sweeping through treetops, the plated stegosaurs with their distinctive spines, the crested hadrosaurs with their haunting calls echoing across wetlands, and the great tyrants of the Cretaceous, whose very names still evoke primal awe. But in the Triassic, they were simply survivors, blending into a busy, competitive crowd of reptiles, lingering amphibians, and strange synapsids that still carried forward from the Permian world. Not everything was a dinosaur. Here's an important reminder worth emphasizing. Not every reptile striding, crawling, or hunting across the Triassic landscape was actually a dinosaur. In fact, most weren't. Many creatures that look convincingly dinosaur-like in fossil form, armored atosaurs with their protective plates, sail-backed phytosaurs lurking in waterways, or fleet-footed Rowisuchians sprinting across open ground, belong to entirely different evolutionary lineages. The early Mesozoic world was filled with evolutionary experiments, some of them spectacularly odd, others hauntingly beautiful. In many ways, the Triassic was like nature's grand rehearsal, an enormous stage where dozens of different body plans and survival strategies competed for staying power, for that elusive quality of being good enough to persist across millions of years. Some of these lineages would vanish completely before the Triassic era even concluded, leaving behind only scattered fossils and the faintest traces of their existence. Others, like those small, upright dinosaurs we've been following, would step quietly but steadily towards center stage. And just to keep proper perspective when picturing this ancient era, try not to imagine every little reptile as a miniature Tyrannosaurus Rex in training, a proto-tyrant waiting to grow into glory. The vast majority of them were pursuing their own unique evolutionary paths, filling their own ecological niches, and most would leave no descendants at all. Evolution is not a ladder leading inevitably toward a single outcome, a straight line marching towards some predetermined goal. It's more like an endlessly branching tree, with countless twigs pruned short by extinction, and others spreading unexpectedly in directions no one could have predicted. In the fading heat of a Triassic day, as the first stars begin to pierce the darkening sky above Pangaea, these early dinosaurs vanish quietly into the lengthening shadows. They're not yet rulers, not yet giants, not yet the stuff of legend, but their quiet, unassuming footsteps echo forward into the deep future. What seems small and utterly ordinary in this moment carries within it the hidden blueprint of an empire, a dynasty that will endure for more than 160 million years. A new world, the Jurassic flourishing. The harsh, unforgiving Triassic world eventually gave way to something fundamentally different, a new chapter in Earth's history that looked and felt transformed. As the Jurassic period unfolded across the planet, the single massive supercontinent of Pangaea began its slow but inexorable breakup. Great rifts opened across the land like wounds in the Earth's crust, carving deep valleys that would over millions of years widen into entirely new oceans. The climate, while still warm compared to modern standards, grew considerably gentler and more hospitable in many regions. Where once there had been endless, monotonous, arid plains stretching to every horizon, now moisture-bearing weather patterns brought life in startling abundance. Rainfall nourished increasingly thick forests of green. Entire landscapes underwent remarkable transformations, evolving into what might genuinely be thought of as the world's first great gardens. This was a land increasingly dominated by ferns, from delicate ground-covering varieties to massive tree ferns reaching impressive heights, by cycads with their palm-like crowns, and by towering conifers that would dwarf most modern trees. Some of these ancient conifers reached truly remarkable heights, forming dense canopies that stretched high above the forest floor, creating multi-layered ecosystems. Beneath them, thickets of ferns spread like verdant carpets, creating a soft green understory. The air grew heavy with humidity in many regions, and morning mist became a regular presence, clinging low to the ground, drifting between massive tree trunks, and softening all the edges of the landscape. To walk through these Jurassic forests, if such time travel were possible, would feel like stepping into another world entirely. Everything would seem simultaneously familiar and utterly alien, verdant and lush, yet populated by plants and creatures that belong to no modern category. It would be quiet in an unfamiliar way, alive with sounds you couldn't quite place, and filled with creatures that would leave their indelible mark preserved in stone for us to discover millions of years later. The sauropods, defying gravity. Among the most extraordinary creatures to ever walk the earth in any era in any ecosystem were the sauropods. If the Triassic had been a world of small, cautious beginnings, the Jurassic was the era when dinosaurs truly tested the absolute limits of size, pushing against the boundaries of what physics and biology would allow. Sauropods grew to lengths and heights utterly unmatched by any other land animals before or since. With necks stretching upward like natural cranes and bodies supported by sturdy column-like legs reminiscent of architectural pillars, they looked almost impossible, as though someone had suspended the normal rules of gravity specifically to allow their existence. Yet their extraordinary design was not only possible, but remarkably efficient, a masterpiece of evolutionary engineering that would dominate terrestrial ecosystems for tens of millions of years. Part of their anatomical secret lay hidden inside their bones. Sauropods possessed an intricate system of air sacs connected directly to their lungs, operating much like the highly efficient respiratory system of modern birds. This arrangement provided two crucial advantages. It allowed for a remarkably efficient, almost continuous flow of oxygen through their bodies, and perhaps even more importantly for creatures of such immense size, it significantly lightened their skeletons without sacrificing structural strength. Their vertebrae, though individually enormous, were honeycombed throughout with air-filled spaces, creating structures that were simultaneously incredibly strong and surprisingly light. This brilliant biological engineering gave them the remarkable ability to grow to truly massive sizes without literally collapsing under their own bulk, a fate that would have befallen any creature attempting to reach such dimensions without these specialized adaptations. Their necks, too, were marvels that deserve appreciation. Long and surprisingly flexible despite their enormous length, they enabled sauropods to sweep across wide swaths of foliage without needing to constantly reposition their massive bodies. It was an energy-efficient feeding strategy perfectly matched to the Jurassic world's newfound abundance of plant life. In these increasingly lush forests, sauropods could feed almost continuously, methodically stripping leaves from conifers, cycads, and ginkgos, instead of competing with smaller herbivores over the same ground-level shrubs and ferns. They reached upward, effectively turning the forest canopy into a vast buffet table that only they could fully access. Their sheer scale meant that very few predators would dare approach a healthy adult, and their herds could gradually reshape the vegetation patterns of entire regions simply through their feeding behaviors. Other paths, diversity in the Jurassic, but not all dinosaurs chose the path of gigantism that the sauropods so dramatically exemplified. While those long-necked giants stretched ever upward toward the sky, other evolutionary lineages explored entirely different possibilities and filled completely different ecological roles. Feathered theropods began to appear with increasing frequency in the fossil record, their bodies adorned with filaments that at first may have served primarily for insulation or perhaps for visual display. These early feathers, relatively simple in structure at first, would later become progressively more complex through evolutionary time, gradually opening the door to entirely new functions and possibilities. The origins of powered flight were being quietly, incrementally rehearsed in these creatures, though true sustained flight still lay millions of years ahead. In the Jurassic skies above these changing landscapes, the earliest true birds began to take their tentative wing. One of the most famous of these transitional creatures is Archaeopteryx, discovered preserved in the exceptionally fine-grained limestone deposits of what is now Germany. With its clearly feathered wings, its long, distinctly reptilian bony tail, and its mixture of avian and dinosaurian features, it bore a striking combination of traits, appearing half reptile and half bird, a living bridge between two great groups. Though it could not soar effortlessly like modern birds, swooping and wheeling through the air with casual grace, it could certainly glide between trees and perhaps flap short distances with considerable effort, a tantalizing preview of what was to come in the evolutionary story of flight. These first experimental ventures into the air mirrored the dramatic changes unfolding on the ground below. Everywhere, in every habitat, this was a world of exploration and innovation, where new forms of life constantly tested new ways of being, new solutions to ancient problems. Predators of the Jurassic also adapted and diversified to match this increasingly lush world. Theropods split into numerous lineages, some becoming swift, agile hunters with long legs and grasping claws perfectly suited for pursuit, others evolving into apex predators with powerful jaws capable of delivering devastating bites. The eternal dance of predator and prey played out across fern-covered meadows and along forest edges, with the thunder of distant sauropod herds often setting the underlying rhythm of life, a percussion that could be felt through the earth itself. Smaller creatures thrived in the shadows of these giants. Early mammals, none larger than modern shrews and most considerably smaller, scurried cautiously through the leaf litter, living nervous, furtive lives while giants strode obliviously above them, creating a world within a world. A Jurassic morning. To truly imagine a morning in the Jurassic is to picture yourself standing in a conifer grove wrapped in slowly dissipating mist. The rising sun sends pale, slanting shafts of golden light through the towering trees, and the air hangs heavy with the rich scent of damp foliage, of growth and decay happening simultaneously. In the distance, you feel rather than hear a deep vibration carrying through the ground beneath your feet, the slow, deliberate, earth-shaking steps of an approaching sauropod, moving unseen somewhere through the dense vegetation. High overhead, branches suddenly sway and rustle as it feeds. The sound soft yet somehow massive, a gentle tearing and chewing that blends with the calls of feathered creatures stirring among the branches, greeting the new day. This was a world of extraordinary balance, a careful equilibrium between enormity and delicacy, where the largest land animals ever to exist peacefully shared space with some of the smallest and most fragile early experiments in flight. The Jurassic Garden was not merely a place of survival, but a place of evolutionary experimentation and innovation, where life found new paths forward in the wake of profound environmental changes. From towering giants that redefined what large could mean to tiny fluttering forms with primitive feathered wings, just learning the basics of controlled flight. It was a time when Earth's ecosystems grew progressively deeper and more intricate. Each layer of life added something new to the harmony of these ancient living forests, creating a complexity that would only increase as time marched forward. The Cretaceous Revolution, when flowers changed everything. The Cretaceous period, the final act in the age of dinosaurs, marked one of the most profound and consequential shifts in the entire history of life on land. If the Jurassic is remembered primarily as an age of giant fern forests and towering conifers, the Cretaceous brought something entirely unprecedented, something that would forever change the rules of terrestrial ecology: flowering plants. Angiosperms, as botanists call them scientifically, began to spread across the fragmenting continents with remarkable speed, and in doing so, they fundamentally rewrote the rules of how ecosystems functioned. With their colourful blooms, nutritious fruits, and rapid growth cycles, they created entirely new opportunities for insects, herbivores, and eventually the predators that hunted those herbivores. The whole food web was about to be reorganized. Flowers were not merely pretty ornaments making the landscape more aesthetically pleasing. They were genuine evolutionary innovations with far-reaching consequences. By attracting insects and other creatures to help spread their pollen, essentially recruiting mobile animals as partners in reproduction, angiosperms established highly efficient partnerships that completely reshaped how plants reproduced and dispersed across landscapes. Instead of relying solely on unreliable wind currents or random chance, flowering plants enlisted entire armies of beetles, primitive flies, and the earliest bees. The world became dramatically more colourful, more fragrant, and more intricately interconnected than ever before. For the first time in Earth's history, the land carried a living tapestry of blossoms and buzzing pollinators, a quiet revolution unfolding literally beneath the feet of the dinosaurs. New grazers for new plants. As the plants diversified explosively, so did the animals that fed upon them. Hadrosaurs, often called duck-billed dinosaurs because of their distinctive broad, flattened snouts, flourished spectacularly during this time, with their shovel-like beaks and hundreds upon hundreds of closely packed teeth forming enormous dental batteries. They were perfectly, exquisitely suited to grind the fibrous stems and tough leaves of flowering plants. Many hadrosaurs carried elaborate crests on their heads, some hollow and remarkably resonant, functioning like natural wind instruments. These crests almost certainly played important roles in communication, producing deep, haunting calls that could roll across floodplains and through forests, allowing herds to maintain contact even when individuals were hidden by tall, dense vegetation. Entire groups of these herbivores could move together in impressive coordination, grazing vast fields of angiosperms much like modern herds of wildebeest sweeping majestically across African savannas. Ceratopsians, the magnificent horned dinosaurs, also thrived in this flowering world, with their dramatic neck frills and intimidating horns projecting forward like weapons. They were among the most visually striking animals to ever walk the earth. Their frills served multiple purposes. Beyond simple defense, They likely functioned as living billboards for visual display, their edges adorned with blood vessels that could flush dramatically with color during social interactions. Imagine a herd of ceratopsians moving across a vast plain covered in flowering plants. It would have been a sight combining both raw power and unexpected beauty. Horns raised alertly, frills shimmering and perhaps changing color in the bright sun, clouds of golden pollen drifting through the air like snow made of sunlight. Meanwhile, the great sauropods had not vanished from the story. In the Cretaceous, they evolved into new forms, particularly the titanosaurs, which became especially widespread across the southern continents. Titanosaurs roamed in herds across what would become South America, Africa, and India, leaving behind trackways that stretch for kilometers in the fossil record, silent testimony to their once vast migrations. Some titanosaur species reached lengths, rivaling even the greatest Jurassic giants, their immense bodies still supported by those characteristic pillar-like legs as they browsed on trees and shrubs. Despite the rise of numerous new herbivore types, the titanosaurs continued to thrive in their ecological niches, their sheer size continuing to keep most predators at a very respectful distance. A fragmented world, regional diversity. This era was also a time of increasing regional distinctiveness and specialization. As the ancient supercontinent Pangaea continued its slow-motion breakup, the continents drifted progressively further toward their modern positions, separated by growing oceans and expanding inland seas. Dinosaur populations became increasingly localized, evolving in relative isolation and developing unique regional characteristics. North America, for instance, was dramatically split by a vast seaway, the Western Interior Seaway, that effectively divided it into two separate land masses, Laramidia to the west and Appalachia to the east. On Laramidia, a truly dazzling variety of dinosaurs evolved, with many different species existing side by side in surprisingly high diversity, sharing habitats in ways that still puzzle paleontologists. In Asia, new forms of feathered theropods appeared with increasing frequency, some small and remarkably bird-like, others experimenting with flight and gliding in different, sometimes quite unusual ways. In the southern continents, titanosaurs dominated the megafauna niches, while other lineages produced their own distinctive, regionally characteristic forms. The Cretaceous was decidedly not a uniform stage with the same actors everywhere, but rather a complex patchwork quilt, with each region developing its own unique evolutionary character, its own cast of players in the grand drama of life. The seas and skies. The seas themselves underwent equally dramatic transformations during this period. Vast inland oceans such as the Western Interior Seaway spread across continental interiors, creating extensive coastlines and shallow marine environments that teemed with life. These warm, productive waters hosted mosasaurs, which had become the apex predators of their marine ecosystems, some growing to truly impressive sizes, as well as plesiosaurs, with their distinctively long necks and swift, powerful fins. Schools of fish darted through the shallows in glittering clouds, while ammonites, those beautiful shelled cephalopods, floated through open waters, their intricately coiled shells recording the chemical signatures of ancient seas in layers of calcite. Primitive seabirds with toothy beaks skimmed the surface, plucking fish from the waves, while pterosaurs soared overhead, some species developing wingspans as wide as a small airplane. Life in the Cretaceous was emphatically not confined to the land alone, but stretched vibrantly across every environment the planet had to offer, from the deepest ocean trenches to the highest mountain peaks. Among the most exciting developments of this dynamic time was the continued evolution and diversification of birds. Descended from small feathered theropods, the earliest true birds of the Cretaceous were progressively refining the demanding art of powered flight. Their wings grew stronger through generations, their feathers became more specialized and aerodynamically sophisticated, and their overall diversity exploded. Some birds adapted to life along shorelines, developing specialized beaks for catching fish. Others occupied forest environments, feeding on seeds, fruits, or insects. Their presence throughout Cretaceous ecosystems was a powerful reminder that not all dinosaurs were confined to terrestrial life on the ground. With each passing generation, the boundary between bird and non-avian dinosaur blurred further and further until eventually the line would all but vanish completely. A Cretaceous dawn. It's remarkably easy to imagine a Cretaceous morning if you allow your mind to drift there. Picture yourself standing on the edge of an inland sea, perhaps the Western Interior Seaway. The air is filled with the complex hum of countless insects, drawn irresistibly to blossoms newly opened in the first gentle light of day. Hadrosaurs shuffle quietly among the flowering plants, their dental batteries grinding steadily as they process tough stems, while juveniles wander close by, staying within protective distance of their parents. A herd of ceratopsians raises their elaborately frilled heads in near unison, the colors of their crests glinting and shifting as they catch the angled morning sunlight. As they move slowly forward to feed, clouds of pollen catch the light like flecks of suspended gold, creating an almost magical atmosphere. In the distance, barely visible through the morning haze, the enormous shadow of a titanosaur moves with ponderous deliberation, as steady and inevitable as a moving hill. Overhead, feathered forms flit energetically between trees, their calls adding to the morning chorus, while a pterosaur glides silently across the shoreline, its shadow racing across the water's surface. This is not a world of monsters locked in constant violent struggle, but rather a world of endless interwoven lives, each species dependent on others in ways both obvious and subtle. The Cretaceous tapestry was far more than just a flourish of flowers and pollinating insects. It represented the dawn of a fundamentally new kind of interconnectedness, offering a genuine preview of ecosystems that would eventually come to closely resemble the ones we know and inhabit today. With flowering plants came energy-rich fruits and nutritious seeds, opening up entirely new ecological niches that mammals and birds would later occupy and eventually dominate. With the explosion of insect diversity came intricate pollination networks that still underpin modern food webs. Dinosaurs, whether duck-billed grazers, horned defenders, or colossal titanosaurs, were integral parts of this shifting picture, actively shaping and constantly reshaping the land with every step, every bite, every track they left behind. Fragility beneath the beauty. And yet, for all its breathtaking beauty and increasing complexity, the Cretaceous carried with it an underlying sense of fragility. The ecosystems were rich beyond measure, but they were also finely balanced, delicately woven together like threads in silk tapestry. A disruption to one part of this intricate web could ripple outward unpredictably, affecting everything else in cascading consequences. That golden snow of pollen drifting peacefully through the air symbolized both abundance and impermanence, a quiet, almost poetic reminder that even the grandest, most successful ages of life are ultimately temporary. Nothing lasts forever, not even empires that span continents and endure for millions of years. The Cretaceous was undeniably a time of innovation, flowering worlds and feathered wings, seas filled with swift hunters, and skies alive with new evolutionary experiments. It was a time when dinosaurs reached their absolute greatest diversity, when ecosystems grew as intricate and interconnected as any that had existed before. And yet, drifting through it all, in the pollen clouds, in the gentle buzz of insects, in the calls of hadrosaurs echoing across wetlands, there was always that subtle whisper of change, that reminder that even this golden tapestry would one day dramatically unravel. The hidden machinery inside a dinosaur. When most people picture a dinosaur, they naturally imagine the outside intimidating teeth, razor-sharp claws, defensive horns, powerful tails. But the true secret of their remarkable 160 million year success lay hidden within, in the internal architecture that allowed them to thrive across dramatically changing environments. For all their spectacular external diversity, dinosaurs shared some truly remarkable internal traits that fundamentally set them apart from the reptiles that came before them and from the cold-blooded lizards and crocodiles that share our modern world. One of the most striking and consequential features was their revolutionary bone structure. Many dinosaurs, particularly the long-necked sauropods and the active theropod predators, had what scientists call pneumatic bones. Bones extensively filled with air sacs that connected directly to their respiratory systems. At first glance, such air-filled bones might seem dangerously fragile, structurally unsound, but this lightness was profoundly deceptive. These air-filled cavities actually strengthened their skeletons in clever ways, while simultaneously reducing overall weight, making movement far more efficient than it would otherwise be. Imagine a long-necked sauropod stretching its neck 20 meters into the sky, higher than a 6-story building. Without this weight-saving system, its neck would have been impossibly, crushingly heavy, dragging the entire animal down. With hollow, strategically reinforced vertebrae, that same neck became manageable, a natural crane sweeping gracefully across forests and plains. But these air sacs were far more than just clever weight-saving tricks. They were integral components of a remarkably sophisticated respiratory system, one strikingly similar to the highly efficient lungs of modern birds. Unlike mammals, which breathe air in and then back out through the same passages in a simple tide-like rhythm, birds and their dinosaur ancestors had a unidirectional flow of air. Fresh, oxygen-rich air moved continuously through their lungs like water flowing through a stream, ensuring a constant and remarkably efficient supply to the bloodstream. This meant far more oxygen could reach their muscles and vital organs, fueling sustained activity at levels far beyond what sluggish, cold-blooded reptiles could ever manage. In the simplest terms, dinosaurs were built from the inside out to be active, energetic animals. Reading the bones, growth and metabolism. Evidence for this high-energy lifestyle appears written directly in their bones themselves, preserved across millions of years for patient scientists to decipher. Paleontologists carefully study growth rings, microscopic lines laid down season by season in bone tissue, functioning somewhat like the annual rings visible in tree trunks. In dinosaur bones, these growth rings reveal patterns of rapid, almost explosive growth, especially during their youth and adolescence. Some species went from tiny, vulnerable hatchlings to massive adults in just a few short years, reaching enormous sizes at a pace that would be absolutely impossible for a cold-blooded reptile, relying on environmental heat alone. This rapid growth required several things simultaneously: a fast, efficient metabolism, a constant and substantial intake of food, and an internal biological engine working continuously at high speed. Chemical isotopes preserved in fossil bones and teeth add yet more fascinating layers to this picture. These chemical signatures, locked into the mineral structure of fossilized tissues, reveal crucial clues about body temperature and metabolic rates. In many dinosaur specimens, the isotopic data strongly suggest elevated, stable body temperatures, far more similar to modern birds and mammals than to contemporary reptiles like lizards or snakes. They were not basking, slow-moving creatures that relied entirely on the sun to warm their bodies before they could become active. Instead, they generated and carefully maintained heat internally, keeping their bodies perpetually ready for bursts of movement, long-distance migrations, or the demanding work of raising and protecting vulnerable young. The warm-blooded debate, it's complicated. The question of whether dinosaurs were truly warm-blooded or cold-blooded has stirred passionate debates among paleontologists for many decades, sometimes generating more heat than light. But the truth, as scientific evidence has accumulated, seems to be both more complex and genuinely more interesting than either extreme position. Dinosaurs were not simply one category or the other, fitting neatly into boxes designed to describe modern animals. They were something in between, or perhaps more accurately, something entirely their own, a metabolic strategy that doesn't map perfectly onto anything alive today. Some scientists describe them as mesothermic organisms, occupying a metabolic middle ground that allowed remarkable flexibility. This approach meant they could sustain considerably higher, more consistent activity levels than typical reptiles, while simultaneously avoiding the enormous constant energy demands that burden modern mammals and birds. A calm, measured way to phrase it might be not hot, not cold, but beautifully, effectively in between. Temperature control. Many solutions. How dinosaurs actively manage their body temperatures is yet another fascinating piece of the puzzle, revealing multiple evolutionary solutions to the same basic problem. Feathers represent the most famous and well-documented temperature regulation strategy. Once thought to belong exclusively to birds, fossilized feathers are now known to have been present in many non-avian dinosaurs as well, scattered across multiple evolutionary lineages. Initially, these were simple, hair-like filaments, excellent for providing insulation, trapping warm air close to the skin. Over evolutionary time, feathers became progressively more complex and structurally sophisticated, branching into veins and developing interlocking barbs and barbules, eventually serving multiple functions including visual display, tactile sensation, and ultimately powered flight. In smaller dinosaurs, particularly those with higher metabolic rates and larger surface area to volume ratios, feathers trapped body heat effectively, helping them maintain steady internal temperatures even during cool nights or in seasonally cold environments. But other dinosaur lineages experimented with very different thermoregulatory tools. Stegosaurs famously carried large, distinctive plates arranged in rows along their backs, while sail-backed species like the enigmatic Spinosaurus displayed tall, dramatic structures supported by elongated spinal processes. For many years, paleontologists confidently suggested these structures acted essentially like radiators, large surface areas useful for absorbing environmental heat or releasing excess body heat. Modern studies utilizing computer modeling and detailed analysis of fossilized blood vessel patterns show the story is considerably more complicated than initially thought. Blood vessels did indeed run extensively through such structures, suggesting some thermoregulatory function, but these same features could also have been powerfully effective tools for visual display or social intimidation. A row of colorful plates or a towering sail could serve both practical physiological functions and important social purposes simultaneously. Just as antlers in deer or manes in lions do today, the truth almost certainly lies in this mixture, structures shaped simultaneously by both internal physiology and the constant external pressures of survival and reproduction. Even body size itself played a crucial and often underappreciated role in temperature regulation. Large animals change temperature very slowly due to their favorable volume to surface area ratio, a concept scientists call thermal inertia. Massive sauropods, for example, may have maintained relatively constant body temperatures throughout day and night cycles simply because their enormous bodies naturally resisted rapid temperature changes. Small dinosaurs, by contrast, with their higher surface area to volume ratios, would have relied far more heavily on external insulation, like feathers, or behavioral strategies, like seeking shade or burrowing. The variety of thermoregulatory solutions across dinosaur lineages reflects their enormous diversity, from tiny bird-like forms weighing mere grams to immense, mountain-sized herbivores weighing many tons. The power within. All of these sophisticated internal adaptations supported behaviors and lifestyles that pushed dinosaurs far beyond the limitations of their evolutionary ancestors. An efficient bird-like respiratory system, allowed sauropods to grow into living skyscrapers, breathing in enough oxygen to power their massive frames even at extreme sizes. Rapid growth rates fueled quick development, allowing vulnerable hatchlings to grow swiftly out of the most dangerous size classes, where predation risk was highest. Elevated metabolic strategies gave predators the stamina needed to pursue swift prey across considerable distances, and provided herbivores with the energy reserves necessary to migrate across vast landscapes in search of seasonal food resources. These were emphatically not sluggish creatures dragging themselves through primordial swamps, as early 20th century reconstructions often depicted. They were dynamic, active animals, living complex, energetic lives. It's genuinely worth pausing here to reflect on how much of this detailed knowledge comes not from direct observation, which is obviously impossible, but from painstaking, careful study of fossils, a thin slice of ancient bone examined under a powerful microscope, the precise shape and distribution of an air cavity within a vertebra, the subtle chemical traces left behind in tooth enamel 70 million years ago. Each tiny detail is a clue, a faint whisper across deep time of how these animals actually lived inside their own skins. Piece by careful piece, like assembling an impossibly complex jigsaw puzzle with most of the pieces missing, the picture gradually comes together, showing us not just empty skeletons mounted in museums, but once beating hearts, blood flowing through vast networks of vessels, and deep breaths that filled ancient lungs with purpose. The poetry of breathing. There is something almost poetic, almost spiritual, in imagining a dinosaur simply breathing. Air passes smoothly through interconnected sacs, flows across specialized lung tissue designed for maximum efficiency, and cycles steadily onward, never stagnant, always in motion. The system is elegant, economical, and remarkably enduring, so enduring in fact that it still exists virtually unchanged today in the birds singing outside our modern windows. When you hear the cheerful call of a sparrow in your garden, or the piercing cry of a hawk circling overhead, you're also hearing the echoes of a respiratory system perfected during the age of dinosaurs, refined across more than 160 million years. So the next time someone asks that classic question, were dinosaurs warm-blooded or cold-blooded, the answer can be offered with a quiet, knowing smile. They were neither, or perhaps more accurately, they were both. They were something fundamentally different, occupying their own unique space in the spectrum of vertebrate physiology, a reminder that life does not always fit neatly into the convenient boxes we create for it. Evolution often takes the middle path between extremes, or creates entirely new paths that we couldn't have predicted. Dinosaurs thrived in that flexible, adaptable space, with bones that literally breathed, bodies that grew at astonishing speeds, and metabolisms tuned to a rhythm uniquely their own. What moved inside them? The hidden machinery of respiration, circulation, digestion, and thermoregulation was just as impressive and worthy of wonder as the dramatic forms they displayed on the outside. Their internal physiology wasn't a hidden weakness or limitation, but rather hidden strength, the unseen biological machinery that successfully carried them through more than 160 million years of Earth's history, across continents, through climate changes, and into virtually every terrestrial habitat the planet offered. To picture dinosaurs only as teeth and claws, as horns and armor, is to miss fully half the story. They were marvels of biology from the inside out, creatures whose very bones tell us through their microscopic structure that they were specifically made for life in motion, for activity and endurance. While the internal machinery of dinosaurs tells one fascinating story, their external coverings tell another equally compelling tale, one of evolution constantly experimenting with new solutions to age-old problems like temperature regulation, protection, and communication. For generations, popular imagination dressed dinosaurs exclusively in scaly reptilian skin, reminiscent of modern lizards or crocodiles. Museum reconstructions and early illustrations depicted them uniformly covered in overlapping scales, gleaming dully under prehistoric suns. And to be fair, this wasn't entirely wrong. Many dinosaurs did indeed possess scales or scale-like skin textures, beautifully preserved in rare instances where fossilization conditions were exceptionally favorable. Fossilized skin impressions from hadrosaurs and various ceratopsians reveal intricate patterns of small, rounded scales arranged in complex, almost geometric patterns across their bodies. Some impressions show larger, more prominent scales interspersed among smaller ones, creating textures that would have been both visually interesting and potentially functional, perhaps providing some degree of protection or helping to regulate moisture loss in arid environments. But the most revolutionary paleontological discoveries of recent decades have dramatically expanded our understanding of what dinosaur exteriors actually looked like. The revelation that fundamentally changed everything was simple yet profound. Many dinosaurs, far more than anyone had previously imagined, were covered not in scales but in feathers. The feather revolution. The first hints of feathered dinosaurs emerged from the spectacularly preserved fossil beds of Liaoning province in northeastern China during the late 1990s, and they sent shockwaves through the paleontological community that are still reverberating today. Suddenly, dinosaurs that had always been reconstructed as scaly reptiles were being unearthed with clear, undeniable evidence of feather-like structures surrounding their fossilized skeletons. These weren't just isolated oddities or evolutionary flukes. Feathers appeared across multiple distinct theropod lineages, from tiny, delicate forms barely larger than modern songbirds to substantial predators measuring several meters in length. The distribution pattern revealed something profound. Feathers were not a late innovation that appeared suddenly in the first birds, but rather an ancient characteristic that had been present in dinosaurs for tens of millions of years before true flight ever evolved. The earliest feathers were remarkably simple structures, more accurately described as hollow, hair-like filaments rather than the complex, branching structures we associate with modern bird plumage. Scientists call these primitive structures proto-feathers, and they likely served primarily as insulation, trapping a layer of warm air close to the skin, much like mammalian fur does today. In the often cool nights of Mesozoic ecosystems, or in temperate regions where seasonal temperature changes were significant, such insulation would have provided crucial advantages, allowing smaller theropods to maintain more stable body temperatures and remain active across a wider range of environmental conditions. Over evolutionary time, across millions of years and countless generations, these simple filaments gradually became more complex and structurally sophisticated. They developed central shafts, then branching barbs extending from those shafts, and eventually the intricate interlocking barbules that give modern feathers their characteristic smooth, aerodynamic surfaces. Each incremental step in this progression offered new possibilities: better insulation, more effective water shedding, increasingly elaborate visual displays, and ultimately the aerodynamic properties necessary for gliding and powered flight. A rainbow world. Perhaps even more remarkable than the mere presence of feathers is the growing evidence that many of these ancient plumes were brilliantly, vibrantly colored. By examining fossilized feathers at the microscopic level, paleontologists can identify preserved melanosomes, the tiny cellular structures responsible for producing pigments in modern birds. The shape, size, and arrangement of these ancient melanosomes can be compared directly with those in living birds, allowing scientists to make surprisingly confident inferences about the actual colors that adorned dinosaurs millions of years ago. Microraptor, a small four-winged dinosaur from early Cretaceous China, appears to have sported an iridescent black plumage, its feathers shimmering with glossy sheens, similar to modern crows or grackles. Sinosauropteryx, one of the very first feathered dinosaurs ever discovered, displayed a striking pattern of reddish-brown and white stripes running the length of its long, elegant tail, a bold pattern that may have served in visual communication or species recognition. Anchiornis, another beautifully preserved specimen, has been reconstructed with remarkable confidence, showing a complex color scheme, black body plumage, highlighted with white accents on the limbs, topped with a distinctive reddish-brown crest, adorning its head like a natural crown. Suddenly, the ancient Mesozoic world transforms in our imagination from a landscape of drab, uniformly brownish-grey reptiles into something far more visually dynamic, a world splashed with colour, where dinosaurs displayed themselves to potential mates, warned off rivals, or perhaps camouflaged themselves among equally colourful vegetation. The mental image shifts from a sepia-toned prehistoric documentary to something vibrant and alive, filled with visual communication and evolutionary artistry. Not all were feathered. It's crucial to emphasize, however, that not all dinosaurs wore feathery coats. The fossil record clearly shows that different lineages solved their survival challenges in dramatically different ways. Large herbivores like sauropods and ceratopsians, with their massive bodies generating and retaining heat through sheer bulk, had little need for additional insulation. In fact, excessive insulation could have been actively problematic, causing dangerous overheating in animals whose bodies were already naturally retaining thermal energy. Skin impressions from these giants consistently show tough, thick hide, textured with various patterns of scales, practical, durable armor, well suited to their enormous size and the mechanical stresses of supporting multi-ton bodies. Some hadrosaurs and ceratopsians may have possessed limited patches of primitive feather-like filaments in specific regions, perhaps along the back or neck, but their bodies were predominantly covered in traditional reptilian scales. The armored dinosaurs, the ankylosaurs with their club tails, and the stegosaurs with their distinctive plates, were veritable fortresses of bony armor and thick protective skin. Their defensive strategies relied on physical toughness rather than metabolic efficiency or temperature regulation, and their fossil remains show no trace whatsoever of feathers or similar structures. So when picturing the dinosaur world, accuracy demands variety. Imagine a Cretaceous landscape, where a brilliantly coloured, feathered theropod stalks alertly through undergrowth, its plumage catching sunlight in iridescent flashes, while nearby a massive scale-covered sauropod browses peacefully among treetops, its skin thick and textured like ancient leather. Both are dinosaurs. Both are supremely well adapted to their respective niches, but they look as different from each other as a hummingbird looks from an elephant. The giants among giants, sauropods revisited. If we're searching for the single most iconic image of the dinosaur age, the one that captures both its grandeur and its almost surreal quality, we need look no further than the sauropods. These were, quite simply, the largest land animals that have ever existed in Earth's entire 4.5 billion-year history, and nothing alive today comes remotely close to matching their extraordinary dimensions. Consider Argentinosaurus, discovered in, as its name obviously suggests, Argentina. Based on the relatively fragmentary remains that have been found, paleontologists estimate it may have reached lengths approaching 35 meters, roughly 115 feet, and weighed somewhere between 70 and 100 metric tons. That's heavier than a dozen adult elephants combined, heavier than most commercial aircraft. Or consider Patagoteton, another South American giant whose more complete skeletal remains have allowed more confident size estimates. This titanosaur likely weighed around 70 metric tons and stretched approximately 37 meters from nose to tail tip, longer than 3 school buses parked end to end. These weren't just large animals, they were architectural impossibilities made flesh, creatures that seemed to violate our intuitive sense of what biology should allow. engineering marvels. How did they achieve such staggering sizes without literally collapsing under their own weight? The answer lies in a suite of remarkable evolutionary innovations, each addressing a specific challenge posed by extreme gigantism. First and most fundamentally were those pneumatic bones we discussed earlier, vertebrae and other skeletal elements extensively hollowed out by air sacs, creating structures that were simultaneously incredibly strong and surprisingly lightweight. A sauropod's backbone was not a solid column of dense bone which would have been unbearably heavy, but rather an elegant network of struts and spaces, engineered with a sophistication that human architects would recognize and admire. Second, their columnar legs, straight pillar-like, positioned directly beneath their bodies, distributed their enormous weight efficiently downward through solid bone directly into the ground. Unlike mammals, which typically have somewhat bent, flexed limbs designed for running agility, sauropod legs were optimized purely for support, functioning essentially like the load-bearing columns in massive buildings. Third, their enormously long necks allowed them to exploit food resources across vast areas without needing to constantly move their massive bodies. A sauropod could stand essentially stationary and sweep its neck across an enormous feeding zone, stripping leaves from an entire grove of trees with minimal energy expenditure, a brilliant solution to the constant challenge of fueling such an enormous body. And fourth, they possessed remarkably efficient digestive systems, enhanced by gastroliths, smooth stones deliberately swallowed and retained in their stomach chambers. These stones, tumbling and grinding against each other, along with partially digested plant material, helped mechanically break down tough, fibrous vegetation, compensating for the fact that sauropods typically swallowed their food without chewing it. They were, in effect, carrying around natural food processors inside their bodies. A different pace of life. Life as a sauropod would have been characterized by certain distinctive rhythms, dramatically different from smaller, more active dinosaurs. Everything would happen more slowly, more deliberately. Each step would be measured and careful, with the ground literally trembling beneath those pillar-like feet. Feeding would be nearly constant. An adult sauropod likely needed to consume hundreds of kilograms of vegetation daily just to maintain its metabolic needs, meaning much of every day would be devoted simply to eating. Movement from place to place would happen gradually, often in coordinated herds that left behind trackways preserved in ancient mudflats. Fossil evidence showing dozens of individuals traveling together, with smaller juveniles carefully positioned toward the center of the group, surrounded protectively by the massive adults. Reproduction would have been fraught with unique challenges. Sauropod eggs, found at numerous nesting sites around the world, were surprisingly small relative to the adults that laid them, typically no larger than a soccer ball, even for the most enormous species. This meant that hatchlings emerged at a tiny fraction of their eventual adult size, vulnerable and requiring years of steady growth to reach the relative safety that came with increasing bulk. The process of growing from a 5-kilogram hatchling to a 70-ton adult was marathon, not sprint, but sauropods accomplished it with remarkable efficiency, growing at rates that would be impossible for truly cold-blooded animals. Herds and footprints. Trackways preserved in stone tell compelling stories about sauropod social behavior. At locations around the world from North America to Argentina to Australia, paleontologists have documented extensive fossil trackways showing clear evidence of group movement. Multiple animals of various sizes walking in the same direction, their footprints overlapping in ways that suggest coordination and social cohesion. Some trackways show smaller juvenile footprints clustered protectively in the center, flanked on all sides by the massive prints of adults. A formation suggesting deliberate protective behavior, remarkably similar to what modern elephants and other social herbivores practice today when traveling through potentially dangerous territory. These frozen moments in time, preserved by lucky coincidence when mud turned to stone, offer us brief but precious windows into actual behavior, not just anatomy. They show us that sauropods weren't solitary wanderers, but social creatures that moved, fed, and raised their young together, finding safety and perhaps social benefits in numbers. A thundering presence. To truly imagine what it would be like to encounter a sauropod herd, close your eyes and try to feel it. First would come the vibrations, transmitted through the earth itself, a deep rhythmic trembling that you'd sense through your feet long before you saw anything. Then the sounds, the creaking of massive bodies in motion, the heavy measured footfalls, the swish of long necks sweeping through foliage, the gentle rumbles of communication passing between individuals, sounds felt in the chest as much as heard with the ears. And finally, the sight itself, enormous forms emerging from the forest, necks rising impossibly high above the canopy, bodies moving with surprising grace despite their monumental size. It would be awe-inspiring in the truest sense of that overused phrase, a sight that would make a human observer feel simultaneously insignificant and privileged, tiny and yet connected to something profoundly ancient and majestic. Sauropods represent perhaps the ultimate expression of the herbivore strategy. Grow so large that virtually nothing can threaten you, and for more than 100 million years, across 3 geological periods and multiple mass extinction events, that strategy worked brilliantly. They were the unchallenged giants of their world, peacefully reshaping landscapes simply by existing within them. Horns and frills. The ceratopsians. If sauropods represent evolution pushing the boundaries of sheer size, ceratopsians, the horned dinosaurs, showcase evolution as artist and engineer, creating some of the most visually spectacular and mechanically impressive skulls in the entire fossil record. The ceratopsian family includes some of the most instantly recognizable dinosaurs ever discovered. Triceratops, with its 3 prominent facial horns and enormous bony frill, has become a cultural icon. But Triceratops was merely one member of a diverse family that experimented endlessly with horn arrangements, frill shapes, and decorative features. Styracosaurus carried an impressive array of long spikes radiating from the edge of its frill like a natural crown. Pachyrhinosaurus had thickened, knobby bosses instead of horns, bony masses that may have been used in head-to-head pushing contests. Cosmoceratops, recently discovered in Utah, holds the record for the most ornamented skull of any known dinosaur, sporting 15 horns and horn-like structures projecting in various directions, a display that seems almost excessive in its elaboration. Form and function. Those impressive frills and horns served multiple overlapping purposes, and paleontologists continue debating the relative importance of each function. Defense was certainly part of the picture. A well-placed horn could deliver a devastating wound to even a large theropod predator, and a solid frill could protect the vulnerable neck from slashing teeth and claws. But defense likely wasn't the whole story, or even the primary story. Many ceratopsian frills were relatively thin and featured large openings called fenestrae, which would have made them rather poor shields against determined attacks. Instead, these structures were probably primarily tools for visual display and social communication. Imagine ceratopsians using their elaborate headgear, much as modern animals use antlers, colourful plumage, or impressive manes, to attract potential mates, to establish dominance hierarchies within herds, to signal health and genetic quality. A ceratopsian, with larger, more symmetrical, more brightly coloured frill, might have been more attractive to potential partners, enjoying greater reproductive success, and thus passing on the genes for impressive display structures. The frills may have been richly supplied with blood vessels, allowing them to flush dramatically with colour during social interactions, turning bright red or deep purple during confrontations or courtship displays, creating living billboards visible from considerable distances. Battle scars and social lives. Evidence preserved in fossilized bone supports the idea that ceratopsians regularly engaged in intraspecific combat, fighting among themselves rather than primarily battling predators. Numerous Triceratops skulls showed distinctive patterns of scarring and healed injuries on their frills and faces, wounds that match precisely with the spacing and angle of Triceratops' horns. These weren't random injuries from predator attacks, but rather specific, repeating patterns suggesting ritualized combat between rivals, males likely competing for territory, mates or social status within the herd. Much like modern bighorn sheep ram their horns together, in spectacular clashes, Triceratops probably locked horns and pushed, testing strength and endurance. Most of these ancient injuries show clear signs of healing, suggesting the combats were rarely fatal, more about establishing dominance than fighting to the death. It paints a picture of complex social dynamics playing out in ceratopsian herds, with hierarchies established and maintained through ritualized displays and controlled combat. A Cretaceous scene. Picture a late Cretaceous floodplain in what is now western North America. A small herd of Triceratops grazes peacefully on low-growing flowering plants, their powerful beaks precisely cropping tough stems. Juveniles stay close to their mothers, their horns still small and their frills not yet fully developed. The morning sun catches the frill of the dominant male, causing it to flush briefly with color, perhaps a warning to a younger male that's wandered too close. In the distance, a herd of Edmontosaurus large hadrosaurs moves through the shallows of a river, their duck-like bills sweeping through aquatic vegetation. The scene is peaceful, almost pastoral, with the only sounds being the gentle grinding of dental batteries, the calls of pterosaurs overhead, and the ever-present hum of insects moving between flowers. Then, almost imperceptibly at first, the Triceratops begin to raise their heads, turning slightly toward the tree line. Their keen senses have detected something the hadrosaurs haven't yet noticed. A subtle shift in posture, horns turning outward in a defensive posture. The calves are gently nudged toward the center of the group. The adults form an imposing wall of horns and frills, presenting a unified front that clearly communicates we see you and we're ready. This is not blind panic, but calculated readiness, the response of experienced animals who understand their strengths and know exactly how formidable they appear when united. The duckbills, hadrosaurs. Among the most successful and widespread herbivores of the late Cretaceous were the hadrosaurs, commonly known as duck-billed dinosaurs due to their distinctive broad, flattened snouts. These were medium to large herbivores, typically measuring 7 to 12 meters in length, and they became remarkably abundant across North America, Asia, and even reaching into Europe and South America. What made hadrosaurs so successful was their almost perfect adaptation to the Cretaceous world of flowering plants. Their most distinctive feature, that broad, toothless beak at the front of their jaws, was ideal for cropping and gathering vegetation efficiently, but the real innovation lay further back in their mouths. Hadrosaurs possessed what paleontologists call dental batteries, tightly packed rows of hundreds of small teeth arranged in multiple layers, functioning together almost like biological grinding plates. As teeth on the chewing surface wore down from constant use, they were continuously replaced by new teeth moving up from below. At any given time, a hadrosaur might have 2,000 teeth in various stages of growth and wear, creating an incredibly efficient system for processing the tough, fibrous plants that dominated late Cretaceous landscapes. Crests and calls. Beyond their remarkable dental adaptations, many hadrosaur species possessed elaborate crests rising dramatically from their skulls, bony structures that came in a bewildering variety of shapes and sizes. Parasaurolophus carried a long curved crest sweeping backward from its skull like a natural horn. Corythosaurus had a tall rounded crest, reminiscent of an ancient helmet. Lambeosaurus displayed elaborate structures that combined tall spines with forward projecting elements. For many years these crests puzzled paleontologists. Theories ranged from the practical enhanced sense of smell, snorkeling equipment for underwater feeding, to the exotic, but detailed study of their internal structure revealed something remarkable. The crests were hollow, containing intricate passages directly connected to the nasal airways. By creating physical models and computer simulations, scientists discovered that these hollow crests functioned essentially as resonating chambers, similar to the tubes in brass musical instruments. When air passed through them during breathing or vocalization, they would have produced deep resonant calls, each species likely having its own distinctive sound signature. Parasaurolophus, with its particularly long crest, could have produced low-frequency sounds that traveled efficiently over long distances, allowing herd members to maintain acoustic contact even when separated by dense vegetation or considerable distance. In the misty dawn of a Cretaceous wetland, the haunting trumpet-like calls of hadrosaurs echoing across the landscape would have been one of the defining sounds of their world. Herding and nesting. Extensive fossil evidence demonstrates that hadrosaurs were highly social animals living in large herds. Bone beds containing thousands of individuals of various ages suggest these herds could be enormous, perhaps comparable to the vast migrations of wildebeest across modern African plains. Nesting sites discovered in Montana and other locations show that hadrosaurs returned regularly to specific breeding grounds, creating colonial nesting areas where dozens or hundreds of nests would be constructed in relatively close proximity. The nests themselves were carefully crafted, circular mounds of earth and vegetation, with bowl-shaped depressions in the center where eggs were laid in neat, organized patterns. Some of the most compelling evidence for parental care in dinosaurs comes from these hadrosaur nesting grounds. Fossilized remains of juveniles found within nest structures show signs of considerable wear on their teeth, indicating they had been feeding for some time. Yet they remained in or near the nest, suggesting parents were bringing food back to their offspring. Active, intentional parental care extending well beyond the hatching period. This revelation fundamentally changed how we think about dinosaur behavior. These weren't simple-minded reptiles that laid eggs and abandoned them. They were attentive parents that invested significant time and energy into raising their young, teaching them, protecting them, and giving them the best possible start in a dangerous world. The predators. Theropods. Every ecosystem needs predators, animals that regulate herbivore populations, eliminate the sick and weak, and maintain the dynamic balance that keeps the whole system healthy and functioning. In the age of dinosaurs, that role was filled primarily by the theropods, a remarkably diverse group ranging from chicken-sized hunters to the most massive terrestrial predators ever to walk the earth. Theropods were characterized by hollow bones, three-toed feet with sharp claws, and in many lineages, increasingly sophisticated grasping hands. They were exclusively bipedal, walking on powerful hind legs while their arms evolved for various specialized purposes, catching prey, manipulating objects, or eventually bearing wings. The group's diversity was staggering. At one end of the size spectrum were tiny predators like Microraptor and Epidexiptrix, barely larger than modern crows hunting insects, small vertebrates, and perhaps fish. At the opposite extreme were giants like Tyrannosaurus rex, Giganotosaurus, and Carcharodontosaurus, apex predators measuring 12 to 13 meters in length and weighing as much as 8 to 9 metric tons. The icon Tyrannosaurus rex. No dinosaur looms larger in popular imagination than Tyrannosaurus rex, and that fame, for once, is thoroughly deserved. This was an animal built on a scale, and with a specialization that pushed predatory design to its absolute limits. Dajul rex possessed the most powerful bite force of any land animal ever measured or estimated. Calculations suggest a bite force exceeding 57,000 newtons, roughly equivalent to the weight of 3 small cars pressing down through those massive jaws. Its teeth were not delicate blades like those of many other predators, but thick, banana-sized spikes designed to crush bone, not merely slice flesh. Fossilized Triceratops bones, bearing distinctive Carex tooth marks, sometimes show punctures that penetrated completely through solid bone, testament to genuinely crushing power. These weren't precision instruments for surgical strikes. They were battering rams wrapped in flesh, designed to deliver catastrophic, overwhelming damage. But T-Rex was far more than just a massive head mounted on powerful legs. Recent research has revealed remarkable subtlety beneath the monstrous exterior. Its relatively small arms, so often mocked in popular culture, were likely quite powerful for their size and may have served specific functions during feeding or mating. Its forward-facing eyes provided excellent binocular vision and depth perception, critical for an active predator, and its sense of smell was exceptionally well developed, with enormous olfactory bulbs suggesting it could detect carrion or track prey across considerable distances. The question of whether T-Rex was primarily an active hunter or an opportunistic scavenger has generated considerable debate. The truth, as so often in paleontology, likely lies somewhere in the middle, with its size, power, and sensory capabilities. T-Rex was certainly capable of hunting actively when opportunity presented itself, but it was also probably perfectly willing to drive smaller predators from their kills or to feast on animals that had died from other causes. Top predators are pragmatic. They take meals where they find them. Other giants, other strategies. T-Rex was not the only giant theropod to rule the Cretaceous world. In South America, Giganotosaurus prowled what is now Argentina, possibly hunting in coordinated groups to bring down the enormous sauropods that still thrived there. In North Africa, Carcharodontosaurus and the enigmatic sailback Spinosaurus competed for dominance in a very different environment: river deltas, wetlands, and coastal regions where fish and aquatic prey were abundant. Spinosaurus, with its elongated crocodile-like jaws filled with conical teeth and its distinctive sail rising from its back, was recently revealed to have been even more aquatic than previously thought. Fossil discoveries showing a powerful paddle-like tail and dense bones designed to reduce buoyancy suggest it spent considerable time actually swimming, diving for fish and other aquatic prey, the only known dinosaur to adopt such a thoroughly semi-aquatic lifestyle. These various giant predators rarely overlap geographically or temporally, each dominating their own region and time period. This distribution suggests that ecosystems could typically support only one apex predator of such extreme size, with the specific identity of that predator depending on local evolutionary history and environmental conditions. Smaller hunters, pack tactics, and intelligence. At smaller body sizes, theropods displayed even greater diversity in form and strategy. Deinonychus and its relatives, the dromaeosaurs, were medium-sized predators famous for their distinctive sickle-shaped claws on their hind feet. These enlarged claws could be raised off the ground while running, then deployed with devastating effect during attacks, slashing at prey with precision. Evidence from multiple fossil sites suggests some of these predators may have hunted cooperatively in coordinated groups, though the exact nature and sophistication of such cooperation remains debated. What's clear is that they possessed relatively large brains for their body size, suggesting enhanced cognitive abilities, keen senses, and perhaps more complex behaviors than their larger, more heavily built relatives. Velociraptors, despite being considerably smaller in reality than their movie portrayals suggest, about the size of a turkey rather than a human, were likely highly intelligent, quick, and dangerous predators in their own right, equipped with that same distinctive claw and hunting in the arid environments of late Cretaceous Mongolia. Other small theropods specialized in different niches entirely. Oviraptorosaurs, with their short, powerful beaks and partially toothless jaws, likely fed on a mixed diet of vegetation, eggs, and small animals. Some possessed elaborate crests and what appears to have been colourful plumage, suggesting rich social and display behaviours. Incredibly, fossils have been found showing oviraptorosaurs in brooding positions atop their nests, their arms spread protectively over eggs in postures virtually identical to modern nesting birds, direct evidence of parental behaviour preserved across millions of years. A predator's world. Life as a theropod predator would have been a constant balance of patience and explosive action. Hours or even days might pass with relatively little activity, resting in shade, conserving energy, perhaps scavenging opportunistically. Then, when opportunity arose, brief moments of intense calculated violence as prey was pursued, caught, and dispatched. For larger predators like Rex, each successful hunt could provide enough food for days or even weeks. For smaller, more active hunters, the pressure to find food would be more constant, requiring regular successful hunts to maintain their higher metabolic demands. Theropods would have needed to be constantly aware of their surroundings, tracking prey, watching for rivals, avoiding larger predators if they were smaller, and generally maintaining the heightened alertness that characterizes all successful predators. Their world was one of calculation and risk assessment, where a single mistake, a miscalculated leap, an injury sustained during a hunt, could mean the difference between thriving and slowly starving. The end, a world transformed. For more than 160 million years, a span of time almost impossible for human minds to truly comprehend, dinosaurs dominated terrestrial ecosystems across the globe. They witnessed the breakup of Pangaea, the opening of new oceans, the rise and fall of mountain ranges, and dramatic shifts in climate from greenhouse warmth to periodic cooling. They evolved from small, cautious creatures into an astonishing diversity of forms, towering herbivores, armored tanks, swift hunters, and eventually into the birds that still surround us today. But even the most successful dynasties eventually end, and for the non-avian dinosaurs, that end came suddenly and catastrophically approximately 66 million years ago at the boundary between the Cretaceous and Paleogene periods. The cause was an asteroid impact of almost unimaginable violence, a rocky body estimated at roughly 10 kilometers in diameter, about the size of a small city, struck what is now the Yucatan Peninsula in Mexico at a velocity exceeding 40,000 kilometers per hour. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously, instantly vaporizing the asteroid itself, the bedrock it struck, and everything within hundreds of kilometers. The immediate effects were apocalyptic beyond description. A fireball expanded outward at supersonic speeds. Tsunamis hundreds of meters high raced across oceans and inundated coastlines on multiple continents. Earthquakes stronger than any in recorded human history shook the planet. But these immediate catastrophes, devastating as they weren't what ultimately caused the mass extinction. The impact ejected trillions of tons of debris into the atmosphere. Pulverized rock, vaporized seawater, sulfur compounds from the target rocks, creating a global cloud that blocked sunlight for months or possibly years. Temperatures plummeted. Photosynthesis ground to a near halt. Plants died back on a massive scale, and with the collapse of primary productivity, food chains collapsed from the bottom up. Large animals, which required substantial amounts of food, were particularly vulnerable. Herbivores starved as vegetation disappeared. Predators starved as prey populations crashed. Animals that had thrived for millions of years found themselves in a world that could no longer support them. What survived, and why? The extinction was selective, in interesting, and sometimes puzzling ways. All non-avian dinosaurs, every single species vanished. Yet many other groups survived, though often greatly reduced in diversity. Mammals, generally small, and perhaps better able to shelter underground or in water, made it through. Crocodilians survived, possibly thanks to their ability to go long periods without food and to survive in aquatic environments that might have been somewhat buffered from the worst effects. Lizards and snakes survived, as did turtles and frogs. And critically, birds themselves, dinosaurs descended from small feathered theropods, also survived. Perhaps their smaller body size, lower food requirements, or ability to disperse and find isolated pockets of resources gave them just enough advantage to persist where their larger relatives could not. In the aftermath, the world was fundamentally changed. The dominant animals of the Mesozoic were gone, leaving ecological niches empty and waiting to be filled. Mammals, which had spent the entire age of dinosaurs in supporting roles, suddenly found themselves with unprecedented opportunities. Over the millions of years that followed, they would rapidly diversify to fill those empty niches, eventually producing the extraordinary diversity we see today, including, ultimately, humans. Living legacy. But while the great dinosaurs of the Mesozoic are gone, they are not truly extinct. Every morning the descendants of those small feathered theropods wake with the dawn. They sing from trees, soar across oceans, dive into rivers, and inhabit every continent including Antarctica. Birds carry within them the living legacy of their dinosaurian ancestors. When a hawk stoops in a hunting dive, when a heron stalks fish in shallow water, when a tiny hummingbird hovers with impossible precision before a flower, they are performing behaviors refined across more than 160 million years of evolution. The next time you see a bird, any bird from the most common sparrow to the most spectacular eagle, take a moment to really see it. You are looking at a living dinosaur, a direct descendant of the most successful group of vertebrates to ever walk the earth. The hollow bones, the efficient lungs, the keen eyes, the feathered covering, all of these are inheritances from deep time, gifts passed down across millions of years and countless generations. The slow fade towards sleep. And now, as our journey through deep time comes to its gentle close, perhaps you feel ready to let these ancient worlds fade back into the past, where they belong. The sauropods lower their impossibly long necks for the final time, heads bowing like ancient trees in a slow-motion fall. The hadrosaurs fall silent, their haunting calls diminishing into echoes of echoes. The great predators settle into stillness, muscles relaxing, eyes closing. The flowering meadows begin to dim as if twilight itself is falling across millions of years, casting long shadows that stretch from the Mesozoic into our present moment. You've walked through 3 geological periods spanning inconceivable expanses of time, watched the rise of giants whose footsteps shook continents, and witnessed the flourishing of life in forms both familiar and utterly alien. You've breathed Mesozoic air thick with humidity and ancient pollen, felt the footfalls of creatures whose bones now lie silent in museum halls under artificial lighting, and glimpsed a world that truly existed, impossibly distant, yet somehow still vibrantly present in fossil and memory. Now let yourself drift gently downward into rest. Let the images soften around their edges and blur like watercolors bleeding into one another. Let the weight of deep time settle over you like the most comfortable blanket imaginable, warm and reassuring. Breathe slowly and deeply, just as those ancient creatures once breathed, their hollow bones filling and emptying in rhythms not so different from your own, connected across an abyss of time by the simple act of drawing breath. There is something profoundly restful, almost meditative, in contemplating such vast stretches of time. Our daily concerns, our immediate anxieties, the worries that seemed so pressing just hours ago, all of these shrink to proper perspective when measured against hundreds of millions of years. The dinosaurs thrived with extraordinary success, adapted with remarkable flexibility, and ultimately vanished. Yet life continued onward. It always continues, always finds new paths forward, And in that continuity there is both humility and a strange deep comfort that settles into the bones. So, rest now. Let the Mesozoic world fade gracefully into pleasant dreams, populated by gentle giants. Let the thunder of sauropod footsteps become the distant rhythm of your own slowing heartbeat, fading gradually into silence. Let the calls of hadrosaurs echo softly and then diminish into perfect stillness. Let the ancient sunlight dim gradually to comfortable darkness, leaving only peace behind. Thank you for joining me on this extraordinary journey through the age of dinosaurs. May your rest be peaceful and undisturbed, your dreams be pleasant and filled with wonder, and may you wake tomorrow just a little wiser about the ancient world that came before us, shaped us, and continues in unexpected ways around us. Until next time, sleep well. The Tyrant's Reign, T-Rex Revisited. The reign of Tyrannosaurus rex, though mighty beyond measure, was finite like all dynasties, and yet the fascination endures, more than a century after its discovery, burning as brightly as ever. Rex continues to inspire awe in scientists, ignite research across multiple disciplines, and capture imagination in ways few other creatures ever have. It is the undisputed poster child of the dinosaur age, not simply because it was impressively big, but because it was extraordinary in every conceivable measure, senses sharper than most predators, strength that could crush bone like breadsticks, adaptability that allowed it to thrive across changing environments, and a presence that dominated its world completely. Imagine then the close of a day in the late Cretaceous. 66 million years ago, dark clouds gather ominously over a vast floodplain, and rain begins to fall in soft, steady sheets that patter against ancient foliage. A tyrannosaur stands alone in the dimming light, its silhouette massive and unmistakable against the gathering storm. Droplets run down the contours of its skull, tracing the ridges and valleys of bone like tears, as it lowers its enormous head toward the ground, nostrils twitching and flaring at a distant scent carried on the wet wind. Each breath it takes mingles with the sound of rain tapping rhythmically on leaves and water pooling in the rich soil beneath. For a moment, just a single precious moment, the tyrant lizard king is quiet, not in pursuit of prey, not locked in combat, but simply existing, a creature in its world, powerful yet vulnerable, as rain whispers over the land it once ruled with such absolute authority. Sensing the world, the inner lives of dinosaurs. When we try to imagine the inner lives of dinosaurs, what they experienced, what they perceived, how they processed their world, the evidence is frustratingly faint but endlessly fascinating. Bones and teeth tell us much about their size and what they ate, revealing diets and hunting strategies. But what about their senses, those windows through which they experienced reality? What about their daily rhythms, the patterns that structured their lives, and even their moments of rest, those vulnerable times when consciousness faded? With careful, painstaking study of fossil skulls, trackways preserved in stone, and nesting grounds buried for millions of years, scientists are beginning to glimpse, however dimly, what it might have been like to actually experience the world as a dinosaur. It is a quieter story than the dramatic narratives of roaring battles or thunderous stampedes that dominate popular imagination. But perhaps it's a truer one, filled with perception, movement, social connection, and the universal need for sleep. Windows into thought, endocasts and brain structure. One of the most revealing sources of information comes from endocasts, impressions of the inner spaces of dinosaur skulls, where their brains once sat, processing sensory information and commanding bodies. By creating careful molds or using advanced scanning technology to image these cavities digitally, paleontologists can estimate the relative size and shape of different brain regions with surprising accuracy. While dinosaurs did not possess brains, as proportionally large as mammals of comparable size, their intelligence was likely different rather than lesser. Certain features stand out with remarkable clarity. In many theropods, the optic lobes were exceptionally well developed, suggesting keen, sharp vision that could track movement across considerable distances. Olfactory bulbs were often enlarged, especially in predators like Tyrannosaurus rex, pointing unmistakably to a powerful, sophisticated sense of smell that could detect prey, rivals, or carrion from kilometers away. These impressions preserved in stone are like fingerprints of behavior, frozen traces of neural architecture. They are clues that reveal whether sight, smell, or hearing dominated a particular dinosaur's sensory world, shaping how it hunted, how it socialized, and how it moved through its environment. Balance and sound, the inner ear's secrets. The inner ear provides another remarkably rich set of clues about dinosaur behavior and capabilities. Tiny, delicate, bony structures preserved in fossils indicate how dinosaurs balanced themselves and what kinds of sounds they could perceive in their acoustic environment. The semicircular canals of the inner ear, which help animals orient themselves in three-dimensional space, were especially well developed in fast-moving theropods, implying quick reflexes, agile movement, and the ability to make split-second adjustments during pursuit or combat. Hearing ranges can also be inferred from the shape and size of the cochlea, the spiral-shaped part of the ear that processes sound waves into neural signals. Many dinosaurs appear to have been particularly sensitive to low frequencies, capable of detecting deep rumbles and calls that carried across long distances through dense vegetation or across open landscapes. Such sounds may have been ideal for communication in environments where visual contact was difficult. A low, resonant call could travel farther and penetrate obstacles better than a high-pitched one, allowing herd members to maintain contact even when separated by considerable distance or thick forest. Moving together, trackways and social life. These sensory adaptations tie closely and intimately to social life, revealing dinosaurs as fundamentally social creatures. Trackways, long chains of fossilized footprints preserved in what were once mudflats, riverbanks, or beaches, sometimes show groups of dinosaurs moving together in parallel lines, their paths coordinated with remarkable precision. These records of ancient journeys frozen in stone millions of years ago suggest coordinated herding behavior, with individuals carefully adjusting their pace to match their neighbors, maintaining formation across considerable distances. In some particularly revealing cases, smaller footprints appear consistently beside larger ones, strongly hinting at young individuals moving alongside protective adults, sheltered within the group. The picture that emerges from these traces is not of solitary wanderers moving randomly across empty landscapes, but of genuinely social creatures navigating their world in company, bound together by invisible threads of communication and cooperation. Their senses, sight to follow movement and recognize individuals, smell to identify kin and detect intruders, and hearing to detect calls and warnings, would have been absolutely vital in keeping such groups cohesive and functional. Raising the next generation, nesting colonies. Nesting colonies add yet more compelling layers to this image of social complexity and cooperation. Fossil sites reveal dozens, sometimes hundreds, of nests clustered in remarkably close quarters, creating what can only be described as dinosaur neighborhoods. Eggs are arranged carefully and deliberately, often in circular patterns that suggest thoughtful construction rather than random scattering or abandonment. In some species, hatchlings clearly remained in the nest for days or even weeks after hatching, their small, delicate bones preserved alongside eggshell fragments, telling stories of extended childhood. Adults likely guarded their nests diligently or actively fed their vulnerable young, behaviors that imply a significant degree of parental care and emotional investment. To raise offspring successfully in colonies requires coordination, communication, and tolerance. The ability to live among neighbors without constant conflict, to share space without constant competition. The fossil record strongly suggests dinosaurs managed this delicate balance with considerable success, creating societies where the young could grow within the relative safety of the group, protected by many eyes and defended by collective strength. The rhythm of days' activity patterns. But what of their daily rhythms, the patterns that structured their time? Did dinosaurs, like virtually all modern animals, follow predictable cycles of activity and rest? Evidence here is more subtle, requiring careful interpretation, but it exists. The structure of fossilized eyes, specifically the sclerotic rings, bony rings that support the eyeball, can reveal whether a species was adapted for day, night, or twilight activity. Some dinosaurs, particularly smaller theropods with proportionally large eyes, show adaptations consistent with nocturnal or crepuscular lifestyles, hunting under the cover of dim light when many prey species might be less alert. Herbivores, meanwhile, may have mixed feeding with rest in sensible patterns, grazing during cooler hours when exertion was less taxing, and resting when the sun was at its strongest and most oppressive. These patterns suggest a practical division of labor across the day and night, spreading activity across the full cycle of 24 hours rather than concentrating it in narrow windows. Even giants need rest. And yes, even the giants, those colossal creatures whose bulk seems almost incompatible with vulnerability, likely needed their naps. While it strains imagination to picture a 70-ton sauropod settling down for a snooze, carefully folding its enormous legs and lowering its massive body, rest would have been as necessary for them as for any other animal with an active metabolism. Perhaps they dozed standing, lock joints holding them upright in a state of reduced consciousness, or shifted their enormous weight carefully onto the ground for brief periods of deeper sleep, the herd keeping watch while individuals rested in rotation. Smaller dinosaurs may have curled into sheltered spots beneath overhanging rocks, in dense vegetation, or in shallow depressions tucking heads beneath arms like modern birds, their feathers providing warmth and protection. Sleep is one of life's fundamental constants, woven into the biology of virtually every complex animal. There is little reason to believe the age of dinosaurs was exempt from this universal need. One could almost say, with a hint of playfulness, that even giants needed their naps, a reminder that for all their size and power, they were still living creatures governed by the same basic biological imperatives as everything else: play, display, and social bonds. Behavioral hints extend even further into subtler territory, signs of play and social interaction that speak to surprisingly complex inner lives. Bite marks on fossils sometimes come not from hunting or predation, but from sparring, practiced duels between individuals of the same species, testing strength and establishing hierarchy without inflicting serious harm. Uneven wear patterns on bones may indicate repetitive movements, as though some dinosaurs regularly engaged in ritualized displays, posturing, head bobbing, or other stereotyped behaviors used in courtship or territorial disputes. In the fossil record, these behaviors appear only as subtle traces, wear patterns, healed injuries, distinctive bone growths. But when pieced together carefully, they suggest animals not terribly unlike those of today, creatures that competed vigorously, displayed elaborately, courted carefully, and raised young with considerable energy and intention. Fragments of a larger story. To step back for a moment, it is genuinely striking how much of this rich story is built not on complete skeletons mounted dramatically in museums, but on fragments, the curve of an ear canal, barely a centimetre long, the angle and spacing of a trackway, the shape and arrangement of a nest. Each fragment is a quiet voice speaking across millions of years, telling us with increasing clarity that dinosaurs were not simply monsters of size and appetite, but animals with senses, rhythms, and societies, creatures that listened intently, watched carefully, and smelled the air with sophisticated olfactory systems. They followed one another across vast landscapes in coordinated migrations, maintained social bonds across their lifetimes, and paused regularly to rest beneath the rising or setting sun, just as we do. If we imagine them at night, under ancient stars arranged in constellations long since shifted, a new and more intimate perspective emerges. Picture this. The moon rises slowly over a plain where a herd of hadrosaurs settles near water, their bodies dark shapes against the silvery surface. Some keep their heads raised alertly, nostrils twitching as they sample the breeze for danger, while others lower themselves into stillness, eyes closing as sleep approaches. A low, rumbling call drifts across the group, answered softly in return, a way of saying, in their language, all is well, rest now. In the distance, a predator pauses, listening intently to those calls, gauging whether to approach cautiously or to move on in search of easier opportunities. And then, for a time, quiet settles in like a blanket. Even in the age of dinosaurs, there were moments like this, moments of calm, when societies rested peacefully under the same stars we see today, when the constant struggle paused briefly, and the world simply existed in stillness. Dinosaurs were not just bones and teeth scattered in sediment. They were living beings shaped by senses refined across millions of years, by patterns learned and inherited, and by connections to others of their kind. Their brains may not have been large by our standards, but they were suited perfectly to their needs, finely tuned by evolution. They could balance on two legs while running at speed, navigate complex terrain, communicate across distances, and raise families with care that extended well beyond hatching. And when the day's demands were finally done, they too would have closed their eyes and let the world drift by, a reminder that even in the Mesozoic, life followed the steady universal rhythm of waking and sleeping. Beyond the land, rulers of sea and sky. The Mesozoic was not only the age of dinosaurs on land, a fact sometimes forgotten in the overwhelming presence of terrestrial giants. The oceans and skies carried their own rulers, equally strange and equally spectacular, though technically not dinosaurs at all, in the strict cladistic sense. While herds of ceratopsians grazed the plains and sauropods swept their necks through forests like living cranes, other reptiles claimed the air above and the seas below with equal success. Together, they created a world filled with teeth and wings, long necks and spiraled shells, multiple forms of flight and swimming, a stage of life more diverse and interconnected than any one group could possibly hold. Masters of the deep, marine reptiles. In the oceans, plesiosaurs and mosasaurs reigned supreme, filling ecological roles that today belong to whales, dolphins, and sharks. Plesiosaurs, with their extraordinarily long necks and paddle-like limbs, looked like something conjured from dreams rather than evolution. Their bodies were sleek and streamlined, beautifully designed for graceful movement through water. Some species carried impossibly extended necks composed of dozens of vertebrae strung together like beads on a string, creating animals that seemed to defy mechanical logic. These creatures swam with a slow, almost ethereal grace, their fore-flippers beating in perfect unison like the wings of a bird underwater, propelling them through ancient seas with hypnotic smoothness. Others in the plesiosaur lineage followed a different evolutionary path, developing shorter necks and massive, powerful heads, trading elegance for raw power. Their jaws lined with sharp, interlocking teeth were perfectly designed for seizing slippery prey, fish, squid, and other marine creatures that darted through the water. Then came the mosasaurs, who emerged later in the Cretaceous and quickly rose to become apex predators of the seas, dominating marine ecosystems with terrifying efficiency. Related not to plesiosaurs but to monitor lizards, making them closer relatives to modern Komodo dragons than to other marine reptiles. Mosasaurs showed how evolution often arrives at remarkably similar solutions through entirely different evolutionary paths. With elongated, muscular bodies, paddle-like limbs, and tails shaped specifically for powerful propulsion, they move through water like scaled torpedoes, combining speed with devastating power. Fossils show they reached immense sizes, some species stretching over 15 meters from snout to tail tip. Their skulls revealed jaws capable of opening extraordinarily wide, aided by double-hinged joints and flexible skull bones that allowed them to swallow large prey whole, a feeding strategy similar to modern snakes, but scaled up dramatically. Fish, turtles, seabirds, and even other marine reptiles all fell into their expansive menu. They were effectively the sharks of their day, roaming warm, shallow seas that covered much of the continents, their presence shaping entire ecosystems. Living clocks, ammonites. Their prey included ammonites, marine mollusks with beautifully coiled shells patterned in spirals that seem almost mathematical in their precision. Ammonites were abundant and remarkably diverse, each shell marking time like a spiral clock frozen in stone. Many carried intricate ridges and patterns etched across their shells, as if evolution had sketched endlessly on their surfaces, experimenting with form and ornament. Their extinction at the end of the Cretaceous was profound and complete, leaving the oceans strangely empty of their forms. But during the age of reptiles, they were everywhere, their forms drifting in the currents like floating ornaments of the sea, vital components of marine food webs. Wings of leather, pterosaurs. Above the oceans, pterosaurs filled the skies with membranous wings and improbable bodies. These flying reptiles were the first vertebrates to master powered flight, accomplishing this feat long before birds or bats ever took to the air. Their wings were fundamentally different from those of birds, made of tough membranes stretched over elongated finger bones, specifically the fourth finger, extended to remarkable lengths, creating a design unlike anything that came before or has appeared since. Some pterosaurs were small and delicate, flitting over coastlines and lakes in search of fish or insects. Their wingspans measured in centimeters. Others were vast beyond belief, reaching wingspans of 10 meters or more, their shadows sweeping across beaches and lagoons like passing clouds. Quetzalcoatlus, one of the largest known pterosaurs, rivaled a small airplane in size, standing as tall as a giraffe when on the ground. To see such a creature lift off would have been like watching a sail come magically alive and drift gracefully into the air, and sight that would have seemed impossible if we didn't have the fossils to prove it actually happened. Crests and communication. Many pterosaurs carried elaborate head crests, some shaped like sails catching wind, others tall and narrow like natural flags, some curved elegantly like scythes. The functions of these distinctive crests remain actively debated among paleontologists. They may have played subtle roles in flight stability, acting as rudders or counterweights, but many scientists believe they were primarily signals, visual displays used for mating, species recognition, or intimidation of rivals. In this way, pterosaurs paralleled the frills of ceratopsians and the crests of hadrosaurs across land, sea, and air. Creatures were sculpted not only by the demands of survival, but by the demands of communication, attraction, and beauty. Engineering flight. Their wings required immense and complex adaptations. The bones of pterosaurs were remarkably light yet surprisingly strong, filled with air spaces like those of birds, creating structures that were both incredibly lightweight and mechanically robust. Muscles anchored firmly to their chests powered their flight strokes with impressive force, while membranes stretched between their bodies, wings, and even legs, creating sophisticated control surfaces for maneuvering through three-dimensional space. They were not simply gliders drifting passively on air currents, but capable, active flyers, soaring on thermals with remarkable efficiency. diving with precision toward prey and covering vast distances across oceans and continents. The skies above the Mesozoic seas were alive with their movements, their cries echoing over waves, adding another layer of sound to the ancient world. A rich tapestry. The presence of these reptiles, alongside dinosaurs, reveals the true richness of the Mesozoic tapestry. Land was not the only theatre of evolutionary innovation and experimentation. In the oceans, plesiosaurs and mosasaurs solved the challenge of aquatic life in dramatically different ways, one with elegant necks and steady flippers creating graceful hunters, the other with streamlined speed and crushing jaws producing ambush predators. In the skies, pterosaurs experimented endlessly with crests, sizes, and hunting strategies, filling every conceivable niche from small insect hunters to ocean fishing giants with wingspans that would dwarf any modern bird. Each group was anatomically distinct, yet all thrived under the same sun, shaped by similar evolutionary pressures of feeding, mating, and moving through their respective environments. For all their differences, they shared remarkable convergent designs: flippers for marine propulsion, streamlined bodies for reducing drag, soaring wings for efficient flight. Life kept arriving at similar solutions that worked, even when starting from entirely different evolutionary beginnings. Evolution, it seems, writes endless variations on a limited number of themes, finding echoes and rhymes in water, air, and land alike. A moment of rest. To imagine this world at rest is to picture something truly extraordinary: starlight glittering on calm waves, the ocean surface dark, smooth, and mysterious. Beneath, the shapes of plesios drift like shadows, their long necks weaving through silver schools of fish with balletic precision. Far below, deeper in the darkness, a mosasaur glides silently, its body undulating with controlled power, jaws opening wide for an ammonite caught unaware, its spiral shell offering no protection. Overhead, wings pass silently against the stars, the silhouettes of pterosaurs gliding across the heavens, their membranes catching faint moonlight. The land may have belonged primarily to the dinosaurs, but the seas and skies were no less alive, no less extraordinary, no less worthy of wonder. These creatures remind us that the age of reptiles was not a single story with one cast of characters, but a symphony composed of different movements played simultaneously across multiple stages. The dinosaurs ruled the land with undisputed authority, but they shared their time with neighbors just as dramatic, just as successful, just as worthy of our fascination, giants of the deep and rulers of the wind. Together, they filled Earth with motion and sound, with wings above and teeth below, in oceans that shimmered under ancient suns and skies that soared with creatures we can barely imagine. And for a moment in deep time, brief by geological standards, but stretching across millions of years, the world belonged to them all, a planet more alien and wonderful than any science fiction could invent. How we know what we know, all of this detailed knowledge, the reconstructed ecosystems, the inferred behaviors, the estimated sizes and metabolisms, stems from fossils, and fossils are fundamentally just stone shaped by life. They are echoes of existence preserved in geology, whispers across time that paleontologists must learn to interpret with extraordinary care and patience. The process of discovering, excavating, studying, and ultimately interpreting dinosaur fossils is an intricate dance of fieldwork, laboratory analysis, and creative reasoning. It requires equal parts physical endurance, technical expertise, and imaginative thinking, and it begins, always, with a simple act of finding something out of place in the landscape. The hunt, finding fossils. Fossil hunting is not glamorous work. Despite what Hollywood might suggest, it involves long, often uncomfortable days under harsh conditions, walking slowly across barren badlands, under a blazing sun that bakes exposed skin, scanning endless stretches of eroded hillsides and rocky outcrops where sedimentary layers have been exposed by millions of years of weathering. Paleontologists look for tiny fragments, a glint of bone weathering out from softer rock, a tooth that's slightly too large or too regular in shape to be a pebble, the distinctive texture of fossilized material that catches the trained eye. Most days yield nothing but sore feet, sunburn, and renewed appreciation for water bottles. But occasionally, persistence pays off in extraordinary ways. A small fragment protruding from a hillside might be the tip of something much larger, a femur, a skull, or even an entire skeleton lying just beneath the surface, waiting patiently for someone to notice it after tens of millions of years. The excavation, patience in the field. Once a significant find is located and identified, the real work begins: excavation. This is not a matter of grabbing shovels and digging frantically like treasure hunters. Instead, it requires meticulous care, proceeding with surgical precision, sometimes advancing only centimeters per day. The surrounding rock, called the matrix, must be carefully removed using tools that range from jackhammers and pickaxes for the initial rough work to dental picks and brushes for the delicate final exposure. Each bone must be mapped in place, its position relative to other bones carefully documented with photographs, sketches, and detailed measurements, because the arrangement itself tells crucial stories about how the animal died, how it was buried, and what happened to it afterward. Fragile bones are often reinforced immediately upon exposure using special consolidants, liquid preservatives that seep into cracks and strengthen the fossil material. Then, before removal, they are carefully wrapped in protective jackets made of plaster and burlap, much like medical casts for broken bones. These jackets protect the fossils during transport from the field site, often remote and accessible only by rough roads or even helicopter, back to museum laboratories where the real detective work can begin. The laboratory, revealing hidden details. In the laboratory, preparators, specialists in fossil preparation, who possess remarkable skill and endless patience, spend months or even years carefully removing the remaining rock matrix from around each bone. Using microscopes, air-powered tools, and occasionally mild acids that dissolve rock without harming fossil material, they reveal the specimen with painstaking care. What emerges is often incomplete fragmentary pieces rather than complete skeletons. Fossilization is a rare process requiring very specific conditions: rapid burial to protect remains from scavengers and weathering, the right chemistry in surrounding sediments to replace organic material with minerals, and millions of years of geological stability to preserve everything intact. Most animals that died in the Mesozoic left no trace whatsoever, their bodies consumed completely by scavengers or decomposed into nothing. The fossils we find represent an infinitesimally small fraction of the creatures that once lived, the lucky few whose remains happen to fall in exactly the right place under exactly the right circumstances. Reading the bones, what fossils reveal, even fragmentary fossils, however, can reveal astonishing amounts of information when studied by experts who know how to read them properly. The size and proportions of bones indicate body size and build, whether an animal was heavy and slow or light and quick. The shapes of joints reveal how limbs moved and what range of motion they possessed. Muscle attachment points, roughened areas where tendons once anchored to bone, show how powerfully muscles could contract and what movements they produced. Teeth tell immediate stories about diet: sharp, blade-like teeth for slicing meat, blunt teeth for crushing vegetation, or specialized forms for specific food types. Growth rings visible in cross-sections of bone, much like tree rings, reveal how quickly an individual grew and sometimes even how old it was when it died. Pathologies, signs of disease, injury, or infection, appear as abnormal bone growths, healed fractures, or erosion patterns, offering glimpses into the hardships individual animals endured and often survived. Rare, Exceptionally preserved specimens provide even more remarkable detail. Soft tissue impressions occasionally survive, showing skin texture with startling clarity. The arrangement of scales, the presence of feathers, even patterns of coloration in some cases. Fossilized stomach contents reveal last meals with astonishing specificity, sometimes including identifiable bones of prey animals or partially digested plant material that can be identified to species level. Coprolites, fossilized dung, might seem unimpressive, even comical, but they provide direct evidence of diet and digestive processes that no amount of speculation could reveal. Trackways capture behavior frozen in time, walking gaits, running speeds calculated from stride length, evidence of herding or solitary movement, even rare moments like a predator's tracks converging with those of potential prey. Technology's eye, modern techniques. Modern technology has revolutionized what we can learn from fossils without even touching them physically. ET scanning allows researchers to peer inside fossils non-destructively, revealing internal structures like brain cases, inner ear anatomy, or the arrangement of air spaces within bones, details that would be impossible to see without cutting precious specimens apart. Computer modeling takes digital data from scans and uses it to test hypotheses about movement, biomechanics, and function. How fast could a Tyrannosaurus actually run without breaking its legs? How did a sauropod's neck move, and what angles could it reach? These questions can now be addressed through sophisticated simulations that would have been pure speculation just decades ago. Isotope analysis of fossil teeth and bones reveals information about diet, environment, and even migration patterns by analyzing the chemical signatures locked into fossilized tissues during life, signatures that vary depending on what an animal ate, what water it drank, and what climate it lived in. The bigger picture, assembling the puzzle. Each fossil is a piece in an enormous jigsaw puzzle, but unlike a typical puzzle, we don't have the box cover to show us what the completed picture should look like, and most of the pieces are missing entirely. Paleontology requires constantly assembling and reassembling partial images, comparing them with living animals, testing hypotheses against new discoveries, and revising conclusions when new evidence demands it. This is not a weakness of the science, but its fundamental nature and its greatest strength. Science advances not by clinging stubbornly to old ideas, but by remaining open to new evidence and willing to revise understanding when that evidence requires it. Dinosaurs have been studied scientifically for nearly 2 centuries now, yet our understanding continues to evolve dramatically with each new discovery. Feathered dinosaurs, once considered impossible and even heretical, are now so well documented that they're taught routinely in elementary schools. Metabolic rates, once assumed to be universally sluggish, are now understood to have been varied and often quite high. Social behaviors, once dismissed as purely speculative, are now supported by compelling physical evidence in the fossil record. Humility and wonder. There is profound humility in recognizing how fragmentary our window into the past truly is, how much remains unknown and perhaps unknowable. But there is also profound wonder in recognizing how much we have managed to learn from stone and bone, how much of the ancient world we have managed to reconstruct from fragments. Every mounted skeleton in a museum represents not just one animal's death millions of years ago, but countless hours of fieldwork under harsh conditions, months of careful laboratory preparation, years of comparative study and analysis, and the accumulated knowledge of generations of scientists who dedicated their lives to understanding creatures they could never see alive. When you stand before a dinosaur skeleton, whether a small, delicate theropod or a towering sauropod whose neck disappears into the ceiling, you are looking at evidence of deep time made tangible, ancient life made visible, and the patient work of science made manifest. Behind every bone is a story not just of what once was, but of how we learned to see it, piece by careful piece. Ancient climates. the world that shaped the giants. Understanding dinosaurs requires more than just studying their bones and reconstructing their bodies. It requires understanding the world they inhabited, the climates they endured, the weather patterns they navigated, and the environmental conditions that shaped their evolution across more than 160 million years. The Mesozoic climate was fundamentally different from our modern world in ways both subtle and profound. For most of the era, Earth was considerably warmer than today, a greenhouse planet with little to no permanent ice even at the poles. Sea levels were higher, continental interiors were more accessible to moisture-bearing weather systems, and temperature gradients between equator and poles were less extreme. A warmer world. During much of the Triassic, Jurassic, and Cretaceous, atmospheric carbon dioxide levels were significantly higher than pre-industrial modern levels, sometimes 2 to 6 times higher, creating a powerful greenhouse effect that trapped heat close to the planet's surface. The results were dramatic and far-reaching. Polar regions, rather than being frozen wastelands locked under ice sheets, were temperate forests where dinosaurs roamed comfortably during long summer days that stretched for months under the midnight sun. Fossil evidence from Antarctica and northern Alaska reveals forests of conifers and ferns, with dinosaurs, including polar-adapted species, living successfully at latitudes where today only specialized Arctic animals can survive. Winter would have brought extended darkness and cooler temperatures certainly, but not the deadly cold of modern polar regions. Instead, these were environments more similar to modern temperate zones, challenging but livable, especially for animals with metabolic strategies capable of maintaining activity through seasonal temperature variations. Seasonal variations and migrations. Even in this generally warmer world, seasons still mattered considerably, especially at higher latitudes where day length varied dramatically. Some dinosaurs may have migrated seasonally, moving toward the poles during summer months, to take advantage of abundant vegetation and continuous daylight, then retreating toward lower latitudes as winter darkness approached. Trackways in Arctic regions show repeated use over time, suggesting established migration routes used generation after generation, much like modern caribou or wildebeest follow ancient paths. The ability to migrate, made possible by their upright stance, efficient locomotion, and elevated metabolism, would have opened up enormous areas of habitat that purely cold-blooded reptiles could never have exploited successfully. Ocean currents and continental drift. Ocean currents played crucial roles in distributing heat around the planet, moderating temperatures and creating regional climate patterns. As the continents gradually drifted apart during the Jurassic and Cretaceous, Pangaea slowly fragmenting into the continental arrangement we recognize today. New ocean basins opened, altering current patterns and creating new climate zones. The opening of the Atlantic Ocean, for instance, fundamentally changed how heat moved between the equator and poles. The formation of the Tethys Sea, a vast tropical ocean that existed between the northern and southern land masses, created warm, shallow marine environments that supported incredible biodiversity and influenced weather patterns across entire continents. These oceanic changes didn't happen overnight in human terms, but over millions of years, yet from the perspective of evolution, they represented significant environmental pressures, constantly pushing species to adapt or face extinction. Volcanic activity and atmospheric changes. The Mesozoic was also a time of significant volcanic activity on truly massive scales. Large igneous provinces, enormous volcanic events that covered vast areas with lava flows, periodically erupted, releasing tremendous amounts of gases into the atmosphere, carbon dioxide, sulfur dioxide, and various other compounds. These eruptions could have rapid and profound climate effects. Initial cooling from sulfur aerosols blocking sunlight, followed by long-term warming from increased greenhouse gases. Some mass extinction events at various points in Earth's history have been linked to such volcanic episodes, demonstrating how dramatically they could disrupt global ecosystems. During the relatively stable middle portions of the Mesozoic, however, moderate volcanic activity likely contributed to maintaining the warm greenhouse conditions that characterize the era, continuously replenishing atmospheric carbon dioxide that would otherwise have been gradually removed by weathering and biological processes. Mesozoic weather, monsoons and storms. What was the weather actually like on a day-to-day basis during the age of dinosaurs? While we can infer general climate patterns from geology and fossil evidence, specific weather conditions are harder to reconstruct with certainty. However, some educated inferences can be made. In the Triassic, with its single supercontinent Pangaea, the interior regions likely experienced extreme continental climates, with intense monsoonal patterns, long dry seasons, followed by violent soaking wet seasons, when moisture finally penetrated inland from distant coastlines. By the Jurassic, and especially the Cretaceous, as continents fragmented and seaways expanded, climates became more moderate and maritime influences reached further inland. Coastal regions would have experienced relatively mild, moist conditions with frequent rainfall supporting lush vegetation. Interior regions would still have been drier, but less extreme than the Triassic deserts. Storms, of course, would have been part of life. Tropical cyclones forming over warm oceans, thunderstorms sweeping across plains, seasonal rains flooding river valleys. Dinosaurs would have weathered these storms much as modern large animals do, seeking shelter when possible, enduring when necessary, and emerging afterward to continue their lives. Climate and evolution, constant pressure. Perhaps most importantly, climate was not static background scenery, but an active force constantly shaping evolution. Cooling periods favored species with better insulation, potentially driving the evolution of feathers in some lineages. Warming periods might favor larger body sizes that could better dissipate excess heat through thermal inertia. Drying trends would favor species capable of extracting maximum moisture from food or traveling long distances to find water sources. Regions that became more humid would see the expansion of species adapted to dense vegetation. In this way, climate acted as an invisible sculptor, continuously molding life to match changing conditions. The dinosaurs that thrived for so long did so not despite environmental change, but partly because they proved capable of adapting to it across vast timescales, migrating, evolving, and finding ways to persist through gradual climate shifts that would have defeated less flexible organisms. The green world, plants of the Mesozoic. While dinosaurs rightly capture most of the attention and imagination, they existed within and depended upon plant communities that were equally distinctive and equally fascinating. The Mesozoic was, after all, fundamentally a partnership between herbivores and plants, predators and prey, each group shaping the evolution of the other in an endless dance of adaptation. Triassic flora, the old guard. In the Triassic, plant life was still dominated by survivors from the Permian and earlier periods, ancient lineages that had weathered the Great Dying and were slowly recovering their former diversity and abundance. Ferns carpeted the forest floors and pioneered disturbed ground, their spores dispersing widely on wind and water. Cycads, with their stout trunks and palm-like crowns of stiff, feathery leaves, grew in groves and thickets, particularly in drier regions where their deep roots could tap distant water sources. Ginkgos, represented today by a single living species, were diverse and widespread, their distinctive fan-shaped leaves carpeting the ground in fall. Conifers were perhaps the most successful trees, reaching impressive sizes and forming the dominant canopy in many regions. Unlike modern conifers that tend toward relatively simple cone shapes, many Mesozoic conifers had spreading crowns and varied growth forms, creating forests that would have seemed simultaneously familiar and subtly alien to modern eyes. What was notably absent from Triassic landscapes were grasses, which wouldn't evolve until much later, and flowering plants, which would revolutionize terrestrial ecosystems when they appeared in the Cretaceous. The Triassic world was green and alive but structured quite differently from modern plant communities. Jurassic forests, lush and layered. The Jurassic saw an explosion of plant diversity and abundance, driven by warmer, moister climates and the continued recovery and diversification of plant lineages. Forests grew taller, denser, and more structurally complex, creating multi-layered ecosystems from ground level to high canopy. Tree ferns became enormous, some reaching heights of 20 meters or more, their spreading fronds creating shady understories. Cycads reached peak diversity, with species adapted to nearly every terrestrial environment from riverbanks to arid highlands. Conifers towered above everything else, their straight trunks rising like natural pillars toward the sky. One particularly notable group was the Araucariaceae, relatives of the modern monkey puzzle tree, which formed vast forests especially in southern continents. These trees could reach tremendous heights with massive straight trunks, creating cathedral-like spaces between them where sunlight filtered down through dense canopies high above. This three-dimensional complexity of vegetation created numerous distinct niches. Ground-dwelling herbivores feeding on ferns and fallen vegetation, mid-level browsers reaching into cycad crowns and lower tree branches, and the great sauropods with their impossibly long necks accessing the highest reaches of the canopy, where few other animals could feed. Cretaceous Revolution, the rise of flowers. Then came the Cretaceous Revolution, one of the most consequential transitions in the entire history of land plants. Flowering plants, or angiosperms, appeared in the fossil record during the early Cretaceous, initially as small, seemingly insignificant herbs and shrubs in disturbed or marginal habitats. But they possessed revolutionary innovations that would soon give them enormous advantages. Flowers for attracting animal pollinators, rather than relying purely on wind, enclosed seeds protected within fruits that could entice animals to disperse them, and faster growth rates that allowed them to colonize disturbed ground rapidly and reproduce more frequently than slow-growing conifers and cycads. Within tens of millions of years, a remarkably short time in geological terms, angiosperms had diversified into thousands of species and transformed landscapes across the globe. By the end of the Cretaceous, they dominated many ecosystems, particularly in disturbed areas, floodplains, and regions with seasonal rainfall patterns. New partnerships, flowers and pollinators. The rise of flowering plants created entirely new ecological relationships. Insects, particularly beetles initially, later joined by bees, flies, and butterflies, became essential partners in plant reproduction. Plants evolved elaborate structures to attract these pollinators, bright colors, enticing fragrances, sweet nectar rewards. In return, insects received reliable food sources, and as they specialized, some species became entirely dependent on specific plant groups, creating intricate co-evolutionary relationships that persist to this day. This partnership between flowers and insects represents one of evolution's greatest success stories, ultimately producing much of the terrestrial biodiversity we see in modern ecosystems. For herbivorous dinosaurs, flowering plants represented new food sources with different nutritional profiles. Many angiosperms grew quickly and could resprout rapidly after being grazed, potentially supporting higher densities of herbivores than slower-growing conifers. Some produced protein-rich seeds and nutritious fruits, creating concentrated food sources that hadn't existed before. Hadrosaurs, ceratopsians, and other late Cretaceous herbivores, with their specialized dental batteries and efficient digestive systems, were perfectly positioned to exploit these new food sources, and their diversity exploded alongside that of flowering plants, in a clear example of coevolution shaping both groups simultaneously. A shifting landscape. To walk through a Cretaceous landscape late in the period would be to experience a world in transition, ancient and modern existing side by side. Towering conifers still dominated some regions, their dark green crowns rising above everything else, remnants of an older world, but at their feet flowering shrubs and herbs created colourful understories splashed with blooms, whites, yellows, purples and reds, attracting buzzing clouds of insects. Along river banks, broad-leaved flowering trees like primitive relatives of magnolias and water lilies spread their leaves to catch sunlight, while in drier uplands cycads and ginkgos held on in reduced numbers, outcompeted in many areas, but persisting in specialized niches where their ancient strategies still worked. The smell of the air would have been different, richer, more complex, filled with floral fragrances that hadn't existed earlier in the Mesozoic. The sounds would have changed too, with the buzz of pollinators becoming a constant background hum, a sound that had been absent or much quieter in earlier periods. Food for giants. All of this plant life, of course, existed to support the herbivores that consumed it in enormous quantities. A single large sauropod might have needed to consume hundreds of kilograms of vegetation daily just to maintain its metabolism. Herds of hadrosaurs or ceratopsians could have cropped entire meadows down to stubble in short order. But plants evolved defenses in response. Tough, fibrous tissues, difficult to digest, chemical compounds that tasted bad or were mildly toxic, spines and thorns to deter browsers. The relationship between plants and herbivores was not passive consumption, but active co-evolution, an arms race where each side constantly adapted to the other's strategies. This dynamic interaction between plant and animal, herbivore and food source, predator and prey, pollinator and flower, created ecosystems of staggering complexity, far more intricate than the simple dinosaurs eating plants narrative suggests. The Mesozoic world was woven from countless threads of interaction, dependency, and adaptation, creating a living tapestry whose patterns we're still working to fully understand. From egg to adult, reproduction and growth, how did dinosaurs reproduce, raise their young, and grow from tiny hatchlings to enormous adults? These questions, which might seem impossible to answer about extinct animals, have been addressed with surprising detail through careful study of nests, eggs, embryos, and growth series, showing individuals at different life stages. Eggs and nests, careful construction. Dinosaur eggs have been found on every continent in a remarkable variety of sizes and shapes. Some were spherical, others elongated. Some had smooth surfaces, others were textured with patterns that might have aided gas exchange or provided structural strength. Sizes ranged from small bird-like eggs, barely larger than a chicken's, to enormous specimens the size of basketballs. Interestingly, even the largest dinosaurs laid relatively modest eggs, nothing approaching the size proportionate to their enormous bodies. This limitation likely resulted from basic physics. Eggshells must allow gas exchange for the developing embryo to breathe, but thicker shells reduce gas exchange. Beyond a certain size, eggs simply couldn't provide adequate oxygen to developing embryos while maintaining structural integrity. This meant that even sauropods weighing 70 tons hatched from eggs, weighing just a few kilograms, creating an enormous growth journey from hatchling to adult that took years or decades of continuous development. Nests themselves show considerable diversity in construction and arrangement. Some dinosaurs, particularly theropods, created simple scrapes in the ground, arranging eggs carefully in spiral or circular patterns that maximize space while allowing the parent to settle atop them for brooding. Others built substantial nests of vegetation, creating mounded structures that might have used decomposing plant material to generate heat for incubation. Colonial nesting sites, where many individuals nested in close proximity, have been found for several species, suggesting social breeding behavior and perhaps cooperative defense against predators. The famous Egg Mountain site in Montana revealed numerous Maiasaura nests with hatchlings, providing some of the most compelling evidence for parental care in dinosaurs. Parental care, staying with the young. The question of parental care, whether dinosaurs simply laid eggs and abandoned them, or whether they actively cared for offspring, has been largely settled in favor of active care, at least in many species. Evidence comes from multiple sources that paint a consistent picture. Hatchling bones found within nest structures show wear on their teeth and joints, indicating they had been moving around and feeding for considerable periods after hatching, yet they remained in or very near the nest, suggesting they were fed and protected there rather than immediately wandering off to fend for themselves. Adult specimens have been found in brooding positions over nests, arms spread protectively over eggs in postures virtually identical to modern ground nesting birds. While some of these may represent animals that died during nesting rather than active brooding, the frequency and consistency of these arrangements strongly suggests intentional protective behavior. Bone beds containing numerous individuals of various ages suggest extended family groups or herd structures where juveniles remained with adults for protection and guidance, not unlike modern elephants, where calves stay with their mothers and aunts for years, learning essential survival skills. Growth rates. From hatchling to giant. Perhaps the most remarkable aspect of dinosaur life history was the sheer scale of growth many species achieved. A titanosaur hatchling, weighing 5 kilograms, needed to reach 50,000 kilograms or more, a 10,000-fold increase in body mass achieved over perhaps 30 to 40 years. Study of growth lines in dinosaur bones reveals that this growth wasn't steady and linear, but typically followed a pattern, relatively slow growth initially, as hatchlings learned to feed and avoid predators, then explosive rapid growth during adolescence, as they quickly passed through the most vulnerable size classes where predation risk was highest, and finally, a slowing or cessation of growth as they reached adult size. This growth strategy, slow, fast, slow, is actually quite similar to modern mammals and birds, and quite unlike typical reptiles that grow slowly and continuously throughout life. It represents another line of evidence that dinosaurs had elevated metabolisms and active life histories more similar to endothermic animals than to modern cold-blooded reptiles. The fastest-growing dinosaurs could gain several kilograms per day during peak growth periods, an astonishing rate requiring enormous food intake and highly efficient metabolic processing. For large theropods like Tyrannosaurus, reaching adult size took only about 20 years, with most of that growth compressed into an intense adolescent growth spurt, lasting just a few years. Challenges of youth. Being a juvenile dinosaur was inherently dangerous, too large to hide effectively yet too small to defend themselves. Juveniles faced predation from numerous sources. Growth marks and healed injuries on juvenile bones suggest many individuals suffered attacks and injuries, though obviously the ones we find as fossils were at least lucky enough to survive and heal. The mortality rate was likely highest among the smallest hatchlings and youngest juveniles, tiny, vulnerable, and appealing prey for a wide range of predators. Those that survived past a certain threshold size would have faced progressively lower predation risk, as they became too large for most predators to tackle safely. This intense selective pressure likely favored rapid growth. Individuals that grew quickly, spending less time in vulnerable size classes, had better survival odds, passing on genes for fast growth to their offspring in a continuous evolutionary feedback loop. Lifespans. How long did dinosaurs live? Determining the lifespan of dinosaurs is challenging but not impossible. Growth lines in bones can be counted much like tree rings, providing minimum age estimates for individuals. The largest individuals of species tend to show slowed or ceased growth, suggesting they had reached full adult size and likely considerable age. Based on these lines of evidence, scientists estimate that large sauropods might have lived 50 to 80 years, or possibly even longer, comparable to modern elephants and tortoises. Large sauropods perhaps lived 30 to 40 years. Smaller species probably had shorter lifespans, maybe 10 to 20 years, though still respectable compared to modern reptiles of similar size. These estimates place dinosaurs firmly in the range of modern large mammals, rather than long-lived reptiles like tortoises, again supporting the view of them as active, metabolically elevated animals with life histories shaped by their distinctive physiologies. Biogeography and isolation. The story of dinosaur diversity cannot be told without understanding the slow-motion dance of continents across the face of the Earth. During the age of dinosaurs, the very ground beneath their feet was moving, imperceptibly to any individual creature, but dramatically over millions of years, reshaping the stage upon which evolution played out. Pangaea's breakup, a fragmenting world. When dinosaurs first appeared in the Triassic, all the world's landmasses were united in the supercontinent Pangaea, one vast expanse of land surrounded by a single planetary ocean. This geographic unity meant that early dinosaur lineages could potentially spread across the entire world, and indeed some Triassic species appear in fossil deposits on multiple modern continents, evidence of their once continuous range. But Pangaea was already beginning to fracture, and by the Jurassic, great rifts were opening like geological wounds. The supercontinent was splitting roughly along an east-west axis, separating into Laurasia in the north, which would eventually become North America, Europe, and Asia, and Gondwana in the south, which would fragment further into South America, Africa, India, Antarctica, and Australia. As these landmasses drifted apart, populations of dinosaurs became isolated from one another. Groups that had once been part of a single interbreeding population found themselves separated by growing oceans that no terrestrial animal could cross. In isolation, they began to evolve independently, diverging into distinct species shaped by their unique local environments and the random processes of mutation and genetic drift. Regional faunas, different worlds. By the late Cretaceous, this fragmentation had produced dramatically different regional dinosaur faunas. North America, for instance, was home to iconic species like Tyrannosaurus, Triceratops, and various hadrosaurs, species that were uniquely North American and found nowhere else on Earth. South America had developed its own distinctive fauna, dominated by enormous titanosaurs, along with unique predators like Giganotosaurus and the unusual herbivore Carnotaurus, with its remarkably short, deep skull and small horns. These animals had evolved in isolation on a southern continent that was following its own evolutionary path. Asia harbored perhaps the most diverse dinosaur fauna, with remarkable feathered theropods, unusual herbivores, and the largest flying creatures ever to exist. In Mongolia and China, fossils reveal ecosystems quite different from contemporary North American ones, with different families dominating and different ecological relationships shaping communities. Even more remarkably, some continents or portions of continents had been isolated for so long that they developed truly distinctive faunas. Madagascar, which separated from mainland Africa during the Cretaceous, hosted unique dinosaur species found nowhere else. Evolutionary experiments playing out on an island stage. Land bridges and dispersal. Yet isolation was never absolute. Occasionally, fluctuating sea levels or temporary land connections would create opportunities for dispersal, brief geological moments when animals could move between previously isolated landmasses, introducing new species and reshaping ecosystems. The Bering Land Bridge, for instance, periodically connected Asia and North America, allowing exchange of fauna between the two continents. This helps explain why some dinosaur groups appear on both sides of the Pacific. They had ancestors that managed to cross during these windows of opportunity before being separated again. Similarly, Connections between North and South America varied throughout the Mesozoic, sometimes allowing exchange, sometimes isolating the continents completely. These intermittent connections created complex biogeographic patterns that paleontologists are still working to untangle. Evolution in isolation. This geographic fragmentation had profound evolutionary consequences. Isolated populations faced different climates, different plant communities, different predators and prey, and different diseases. Natural selection pushed them in different directions, gradually transforming what had once been variations within a single species into distinct species that could no longer interbreed, even if reunited. In some cases, isolation led to remarkable parallel evolution, distantly related dinosaur lineages, independently evolving similar solutions to similar problems, creating species that looked superficially similar despite having different evolutionary origins. Duck-billed hadrosaurs in North America and some South American herbivores, for instance, both evolved elaborate dental batteries for processing tough vegetation, despite not being closely related. The shifting continents also created opportunities for dramatic diversification. When a landmass split, populations on each fragment suddenly had access to resources and niches formerly occupied by others. This ecological release could trigger rapid evolution as species adapted to fill newly available roles. Reading biogeography and fossils. Today, the distribution of fossil species across continents provides crucial clues about ancient geography. When paleontologists find closely related species on continents that are now separated by oceans, it suggests those land masses were once connected. The timing of when species diverge helps establish when continents separated. For instance, the distribution of certain sauropod families makes sense only when you understand that South America, Africa, and India were still connected during the Jurassic, forming the core of Gondwana. As these continents separated, their sauropod populations diverged, eventually producing the distinctive titanosaurs that would dominate southern continents through the late Cretaceous. Biogeography thus becomes a tool for reconstructing not just the history of life, but the history of the Earth itself, the two stories inextricably woven together, each helping to illuminate the other. The day the world changed, mass extinction. For 160 million years, dinosaurs dominated terrestrial ecosystems across the globe with remarkable success. They had weathered climate changes, adapted to new plant communities, diversified into countless forms, and spread across every continent. By any measure, they were among the most successful groups of animals ever to exist. And then, approximately 66 million years ago, in a geological instant, it all came crashing down. Impact winter. When the sky fell si full. The immediate cause of the extinction has been established with considerable certainty. A massive asteroid or comet struck Earth near what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater, a scar on the planet measuring roughly 150 kilometers across. The object itself was perhaps 10 to 15 kilometers in diameter, traveling at speeds exceeding 20 kilometers per second when it struck. The impact released energy equivalent to billions of nuclear weapons detonating simultaneously, an explosion so violent it beggars description. The immediate effects were apocalyptic on a truly planetary scale. Everything within hundreds of kilometers was instantly vaporized or incinerated. The impact ejected trillions of tons of debris into the atmosphere, pulverized rock, vaporized seawater, sulfur compounds from the bedrock, creating a global cloud that enveloped the entire planet within days. This shroud of dust and aerosols blocked sunlight for months, possibly years. Temperatures plummeted in what scientists call impact winter. Photosynthesis ground to a near halt across the planet. Without sunlight, plants died back massively. Without plants, herbivores starved. Without herbivores, predators starved. The food chains that had sustained life for millions of years collapsed from the bottom up. Large animals, which required substantial daily food intake, were particularly vulnerable. Dinosaurs, which had evolved and thrived in a world of plenty, found themselves in a world of scarcity where their very success became their weakness. The volcanic factor, adding insult to injury. But the story may be more complex than a single catastrophic impact. Around the same time, massive volcanic eruptions were occurring in what is now India, the Deccan Traps, which poured out enormous volumes of lava over extended periods. Some scientists argue these eruptions may have already stressed ecosystems before the asteroid struck, making them more vulnerable to the final catastrophic blow. Others suggest the impact itself may have triggered or intensified volcanic activity on the opposite side of the planet through seismic shockwaves. The truth likely involves both factors acting together, a geological one-two punch that ecosystems simply couldn't withstand. Volcanic gases altered atmospheric chemistry, potentially causing acid rain and gradual warming. The asteroid impact then delivered the final devastating blow that pushed already stressed ecosystems past their breaking point. Selective survival. Why did some live? The extinction was remarkably selective in ways that still puzzle scientists. All non-avian dinosaurs vanished. Every single species from the smallest to the largest. Yet many other groups survived, often with substantial losses but not complete extinction. Crocodilians made it through, perhaps thanks to their ability to survive long periods without food and their semi-aquatic lifestyle that may have buffered them from the worst effects. Small mammals survived, possibly because their small size, lower food requirements, and ability to shelter underground or in water gave them crucial advantages. Birds, technically dinosaurs themselves, also survived, though many lineages went extinct. The surviving bird lineages were apparently those with characteristics suited to survival in harsh conditions, perhaps ground-dwelling species that could find food in devastated landscapes, or water birds that could exploit aquatic resources less affected by the collapse of terrestrial ecosystems. Turtles, lizards, snakes, amphibians, and freshwater fish all survived in significant numbers. The pattern suggests that small body size, low metabolic demands, and ability to shelter or access alternative food sources were key survival traits in the immediate aftermath of the impact. The gradual versus sudden debate. An ongoing scientific debate concerns whether dinosaur extinction was truly instantaneous or whether they were already declining before the asteroid struck. Some fossil evidence suggests dinosaur diversity was decreasing in the final few million years of the Cretaceous, with fewer species present than in earlier times. However, this apparent decline may be an artifact of the fossil record. There are simply fewer fossil-bearing rocks from the very end of the Cretaceous, making it difficult to assess true diversity accurately. The debate continues as scientists refine dating techniques and discover new fossil sites. What remains clear is that even if dinosaurs were facing some environmental pressures before the impact, they were still diverse, widespread, and successful right up until the very end. The asteroid impact was not a mercy killing of animals already doomed, but rather a catastrophic event that destroyed ecosystems supporting thriving, successful species. The world transformed. In the aftermath, the world was fundamentally different, quieter, smaller, emptier. The great herds were gone. The thundering footsteps ceased. The calls that had echoed across landscapes for 160 million years fell silent forever. Slowly, very slowly, life began to recover. Plants recolonized devastated landscapes. Surviving animals emerged from refugia and began to spread, and among those survivors were mammals, which had spent the entire Mesozoic as small, mostly nocturnal creatures, living cautiously in the shadows of giants. With the dinosaurs gone, ecological niches stood empty. enormous opportunities waiting to be filled. Mammals diversified explosively in evolutionary terms, rapidly developing new forms to fill roles previously occupied by dinosaurs. Within 10 million years, barely a moment in geological time, mammals had produced everything from tiny shrews to creatures the size of modern deer. The age of dinosaurs had ended. The age of mammals had begun, but the dinosaurs hadn't vanished entirely, as we shall see. The survivors, birds as living dinosaurs. Here's a revelation that still surprises many people. Dinosaurs didn't actually go extinct. They're all around us, singing from trees, soaring over oceans, and waddling across Antarctic ice. We call them birds. This isn't poetic metaphor or loose terminology. Birds are, in the strictest scientific sense, dinosaurs, members of the theropod lineage that survived the mass extinction and subsequently diversified into the roughly 10,000 species we see today. Every robin, every eagle, every penguin and ostrich is a living dinosaur, carrying forward a lineage that stretches back to the Triassic. From dinosaur to bird, a gradual transition. The evolution of birds from non-avian dinosaurs wasn't a sudden transformation, but a gradual series of modifications over millions of years. Many features we consider quintessentially bird-like actually evolved long before true birds appeared, in dinosaurs that could not fly. Feathers, as we've discussed, appeared first in small theropods for insulation and display, only later being co-opted for flight. Hollow bones filled with air sacs evolved in dinosaurs for weight reduction and respiratory efficiency. Wishbones, fused clavicles that in modern birds anchor powerful flight muscles, first appeared in non-avian theropods. Even brooding behavior, where parents settle over eggs to keep them warm, was present in non-avian dinosaurs. By the late Jurassic, creatures like Archaeopteryx had appeared, animals that perfectly straddled the line between dinosaur and bird, possessing a mixture of features from both groups. They had feathered wings capable of flight, but also long bony tails, teeth in their jaws and clawed fingers on their wings. They were evolutionary intermediates, beautifully illustrating the gradual nature of major evolutionary transitions. Flight. Multiple experiments. Interestingly, powered flight may have evolved multiple times independently within different theropod lineages. Some small dinosaurs like Microraptor had 4 wings, flight surfaces on both their arms and legs, suggesting they were experimenting with flight in ways quite different from modern birds. Others may have been primarily gliders, using feathered surfaces to move between trees or escape predators without achieving true powered flight. The fossil record shows considerable experimentation with aerial locomotion, multiple evolutionary lineages testing different solutions to the challenge of moving through air. Modern birds descended from one particularly successful lineage of flying theropods that survived the mass extinction. In the Paleogene period that followed, they diversified rapidly to fill ecological roles left vacant by extinct dinosaurs and pterosaurs, eventually producing the enormous diversity we see today. Living dinosaurs. Seeing the connection. Once you understand that birds are dinosaurs, you start seeing their dinosaurian heritage everywhere. The way a chicken walks, head bobbing with each step, is the same gait used by many bipedal dinosaurs. The scales on a bird's legs and feet are evolutionary holdovers, modified versions of the scales that covered their dinosaurian ancestors. Ground-dwelling birds like ostriches and emus, which have secondarily lost the ability to fly, look remarkably similar in overall body plan to non-avian theropods. Long powerful legs, relatively small arms, forward-projecting heads, and balanced horizontal postures. They're living windows into what small to medium-sized theropods might have looked and moved like. Even bird behavior echoes their dinosaurian past. Elaborate courtship displays with dancing, calling, and showing off colorful plumage parallel the display behaviors we infer for crested hadrosaurs and frilled ceratopsians. Nesting behavior, territorial defense, and parental care all have roots reaching back into the Mesozoic. A continuous lineage. The key insight is that there was never a sharp dividing line, never a moment when dinosaurs became birds. There was only a continuous lineage gradually accumulating modifications, with evolution smoothly transitioning from one form to another across millions of years. Scientists don't classify birds as descendants of dinosaurs, but rather as dinosaurs themselves, specifically members of the clade Avialae within the larger group Theropoda. Saying birds are dinosaurs is as accurate and scientifically correct as saying humans are mammals or snakes are reptiles. This means the age of dinosaurs never truly ended. It merely changed form, downsizing dramatically and taking to the air, but continuing forward without interruption. Every time you hear birdsong at dawn, you're hearing the voice of dinosaurs, a 230 million-year-old lineage, still thriving, still evolving, still filling the world with life. The next time you see a bird, any bird, take a moment to really observe it. Watch how it moves, how it holds its body, how its eyes track movement with sharp intelligence. You're not looking at something merely related to dinosaurs. You're looking at a dinosaur itself, a direct continuation of one of Earth's most successful evolutionary lineages, carrying forward a legacy that spans the depths of time. The human story, discovery and understanding. Our modern understanding of dinosaurs didn't emerge fully formed. It was built gradually, piece by patient piece, over nearly 2 centuries of discovery, debate, occasional controversy, and continuous refinement. The history of how we came to understand these ancient creatures is itself a fascinating story of human curiosity, scientific progress, and changing perspectives. Early discoveries. A new word for ancient giants. The first scientifically described dinosaur was Megalosaurus, named in 1824 by William Buckland based on fragmentary fossils found in England. At the time, no one understood what kind of creature they were looking at. The very concept of dinosaur didn't yet exist. In 1842, British anatomist Richard Owen recognized that several large fossil reptiles recently discovered shared certain distinctive characteristics, particularly in their hip and limb structure. He proposed grouping them together under a new name, Dinosauria, meaning terrible lizard, not terrible in the sense of frightening necessarily, but terrible in its older meaning of awe-inspiring or terrifyingly great. Owen's initial conception of dinosaurs was quite different from modern understanding. He imagined them as essentially gigantic lizards, slow-moving and sprawling, living in swamps where water would help support their weight. This image, dinosaurs as sluggish, primitive reptiles, would dominate popular imagination for over a century. The Bone Wars. Competition drives discovery. The late 19th century saw an explosion of dinosaur discoveries in North America, driven partly by intense personal rivalry between 2 paleontologists, Edward Drinker Cope and Othniel Charles Marsh. Their bitter competition, dubbed the Bone Wars, led to frantic, sometimes reckless excavation of fossils across the American West. While their rivalry was often petty and occasionally destructive, it resulted in the discovery and description of numerous iconic dinosaurs, including Stegosaurus, Triceratops, Allosaurus, and Apatosaurus, originally and famously misnamed Brontosaurus. These discoveries captured public imagination and established dinosaurs as cultural icons. The Dinosaur Renaissance. A new understanding. For most of the 20th century, dinosaurs were viewed as evolutionary failures, slow, dim-witted reptiles that had become extinct because they couldn't compete with superior mammals. They were presented in museums as tail-dragging, sluggish creatures, interesting primarily as curiosities from a vanished world. This view began to change dramatically in the 1960s and 1970s, during what became known as the Dinosaur Renaissance, led by paleontologist John Ostrom and his student Robert Bakker. They argued, based on anatomical evidence, that many dinosaurs were actually active, dynamic animals with elevated metabolisms, quite unlike modern reptiles. Ostrom's study of Deinonychus revealed a predator clearly built for speed and agility, with features suggesting an active lifestyle incompatible with cold-blooded physiology. This sparked renewed interest in dinosaur biology and behavior, transforming them from evolutionary footnotes into fascinating subjects of serious scientific inquiry. Feathered dinosaurs, revolution from China. The most dramatic shift in understanding came in the 1990s, with discoveries from the Liaoning province of China. Exceptionally preserved fossils began revealing dinosaurs with clear evidence of feathers, simple filaments in some species, complex flight feathers in others. These discoveries were initially controversial. Some scientists refused to believe dinosaurs could have feathers, seeing it as incompatible with their nature as reptiles. But the evidence became overwhelming as more and more feathered dinosaurs were discovered, eventually forcing a complete reassessment. Today, we understand that feathers were widespread among theropods and possibly present in other dinosaur groups. Museum displays worldwide have been updated to show feathered dinosaurs, and popular culture is slowly catching up with scientific reality. Ongoing discoveries. The story continues. Dinosaur paleontology remains an active, vibrant field, with new discoveries regularly reshaping understanding. On average, a new dinosaur species is described every couple of weeks. Species from all over the world, from all periods of the Mesozoic, filling in gaps in our knowledge. New techniques like CT scanning, isotope analysis, and computational modeling allow scientists to extract more information from fossils than ever before. Questions that seemed permanently unanswerable. What colors were dinosaurs? How fast could they run? What did they sound like? Are now being addressed with actual data rather than pure speculation. The story of dinosaurs isn't a closed book from a dead past. It's an ongoing investigation, constantly evolving as new evidence emerges and new techniques become available. Each generation of paleontologists sees these ancient animals slightly differently, building on the work of their predecessors while correcting old errors and adding new insights. Bringing them to life, the art of paleoart. Scientific papers with their technical terminology and detailed measurements are crucial for advancing knowledge, but they're not how most people encounter dinosaurs. Instead, most of us first meet these ancient creatures through art, paintings, sculptures, museum displays, and film that attempt to visualize what living dinosaurs might have actually looked like. This art form, called paleoart, occupies a fascinating intersection between science and imagination, requiring both technical knowledge and creative vision to transform dry bones into living, breathing creatures. The challenge of reconstruction. Reconstructing the appearance of an extinct animal from fossilized bones is extraordinarily challenging. Fossils preserve hard tissues, bones, teeth, sometimes scales or feathers, but soft tissues like muscles, organs, fat deposits, and skin usually vanish without trace. Paleoartists must infer these soft tissues by comparing dinosaur skeletons with modern animals, identifying muscle attachment points on bones, and understanding biomechanics. They study living reptiles, birds, and mammals to understand how muscles, skin, and other soft tissues relate to underlying bone structure. But even with careful study, much remains uncertain. How much fat did a particular dinosaur carry? Exactly what skin texture covered different body parts? What colors and patterns decorated their exteriors? These questions often have no definitive answers, requiring informed speculation based on general principles. Evolution of paleoart. Early dinosaur reconstructions often look bizarre to modern eyes, incorrectly proportioned, posed in impossible positions, or given anatomical features we now know they couldn't have possessed. This wasn't due to incompetence, but reflected the limited knowledge available at the time. As understanding improved, reconstructions became more accurate. The transition from tail dragging to horizontal postures in the 1970s transformed how dinosaurs were depicted. The addition of feathers to theropods in the 1990s and 2000s created another dramatic shift. Each advance in scientific understanding ripples through paleoart, gradually bringing us closer to how these animals actually appeared. The importance of speculation. Interestingly, paleoart's speculative elements aren't weaknesses, but strength. By visualizing possible appearances and behaviors, artists help scientists and the public think about dinosaurs as living animals rather than abstract collections of bones. Moreover, artistic reconstructions sometimes inspire scientific hypotheses. An artist wondering, how did this creature use this structure, might inspire a paleontologist to investigate biomechanics or function. The interplay between art and science is bidirectional, each enriching the other. Impact on culture. Paleoart has shaped how billions of people understand dinosaurs and prehistoric life. Iconic images, the Tyrannosaurus confronting Triceratops, the long-necked Brachiosaurus reaching into treetops, the sickle-clawed Velociraptor poised to strike, have become embedded in global culture, inspiring generations of future scientists and maintaining public interest in paleontology. Films like Jurassic Park, while taking considerable artistic license, exposed vast audiences to dinosaurs presented as dynamic, intelligent animals rather than sluggish monsters. Even scientifically inaccurate depictions serve a purpose, sparking interest that can lead to deeper learning. The best paleoart balances scientific accuracy with aesthetic appeal, creating images that are both informative and emotionally resonant, allowing us to connect across time with creatures we can never see alive, bridging 66 million years through the power of informed imagination. What we still don't know, enduring mysteries. For all we've learned about dinosaurs, profound mysteries remain, questions that may never have definitive answers, gaps in our knowledge that remind us how fragmentary our window into the past truly is. These uncertainties aren't failures of science, but rather honest acknowledgements of the limits of what fossilized bones can tell us. The color question. While we've made progress identifying colors in some exceptionally preserved feathered dinosaurs, we still know almost nothing about what most dinosaurs looked like. Were they drab and camouflaged, or brightly colored and patterned? Did they have dramatic sexual dimorphism with males and females looking quite different? Did juveniles have different colors than adults? For non-feathered dinosaurs, we have virtually no direct evidence of coloration and must rely on informed speculation based on ecology and behavior. A forest-dwelling herbivore was probably camouflaged with greens and browns, while an open plains predator might have been countershaded like modern lions. But these are educated guesses, not proven facts. Behavior and intelligence. Brain size and structure can give rough estimates of cognitive capability, but they can't tell us about personality, problem-solving ability, or complex behaviors. Were some dinosaurs playful? Did they recognize individuals and form social bonds? Could they learn from experience and modify their behavior accordingly? Trackways and nesting sites provide glimpses of behavior, but their static snapshots of moments long vanished. The rich, complex behavioral lives these animals almost certainly lived remain largely invisible to us, lost in the vast gulf of time. Sounds and communication. What did dinosaurs sound like? The hadrosaur crests likely produced sounds, but exactly what those calls sounded like remains uncertain despite mathematical modeling. Did Tyrannosaurus roar like in movies or produce lower frequency rumbles like elephants? Did small feathered theropods chirp and trill like modern birds? Soft tissues of vocal organs don't fossilize, leaving us to infer from anatomy and modern analogues. Educated guesses can be made, but the actual symphony of Mesozoic soundscapes, The calls echoing across plains and through forests remains hauntingly silent in the fossil record. Soft tissue details. Beyond color, countless soft tissue details remain unknown. Did some dinosaurs have distinctive markings, dewlaps, inflatable throat pouches, or other display structures that left no trace in bone? Did they have elaborate courtship rituals? What did their internal organs look like, and how did they function? Exceptionally rare soft tissue preservation provides occasional glimpses, but for most species, these aspects remain entirely speculative. We reconstruct muscles and basic body outlines with reasonable confidence, but the fine details that would make each species truly distinctive as living animals are mostly lost. Why them and not others? Perhaps the deepest mystery concerns extinction itself. Why did non-avian dinosaurs vanish while birds, crocodilians, and many other groups survived? We understand the immediate cause, the asteroid impact, but why it affected different groups so differently remains debated. What specific factors separated survivors from victims? These questions may never be fully answered, yet the mysteries don't diminish what we've learned. Rather, they add depth, reminding us that for all our scientific progress, the past remains fundamentally foreign country, one we can visit only through fragmentary evidence, never fully experiencing it as it truly was. The gift of deep time. Final reflections. As we near the end of our journey, it's worth reflecting on what the story of dinosaurs offers us beyond fascinating facts and impressive statistics. These ancient creatures, long vanished from living landscapes, still teach us profound lessons about life, time, and our place in the universe. Perspective through time. Dinosaurs thrived for 160 million years, a span so vast that human minds struggle to truly comprehend it. Modern humans have existed for perhaps 300,000 years. Recorded human history spans merely 5,000 years or so. The entire history of human civilization is a mere blink compared to the reign of dinosaurs. This perspective is simultaneously humbling and oddly comforting. Our individual concerns, anxieties, and struggles, which feel so overwhelming in the moment, shrink to proper proportion when viewed against such expanses of time. The dinosaurs remind us that we are part of something far larger and older than ourselves, participants in a story that began long before us and will continue long after. Resilience and adaptation. The dinosaurs' long success demonstrates the power of adaptation and flexibility. They survived climate changes, continental drift, the rise and fall of different plant communities, and countless other environmental shifts. They did so by evolving, by finding new solutions to new challenges, by filling every available niche with remarkable creativity. Their eventual extinction, sudden and catastrophic, reminds us that even the most successful groups can fall to events beyond their control, but their 160 million year run, and their continuation in the form of birds, demonstrates that adaptation and resilience can carry life through almost anything. Wonder and curiosity. Perhaps most importantly, dinosaurs inspire wonder, that precious feeling of awe in the face of something vast and extraordinary. In our modern world of constant information and instant answers, genuine wonder has become rare. But stand before a mounted Tyrannosaurus skeleton, or hold a fossilized tooth in your hand, and wonder returns. This wonder motivates curiosity, drives learning, and reminds us that the universe is far stranger and more marvelous than our daily routines might suggest. It connects us to our childhood selves who gazed at dinosaur books with wide-eyed fascination, and it connects us forward to future generations who will continue exploring, discovering, and marveling at these ancient giants. Continuity of life. Finally, dinosaurs teach us about continuity, the unbroken thread of life connecting past, present, and future. The birds outside your window carry DNA passed down through countless generations stretching back to the Triassic. You and those birds share ancestors in the deep past. All life on Earth is family, connected through descent with modification across billions of years. This recognition of continuity and connection can foster a sense of kinship with the natural world, a recognition that we're not separate from nature but part of it, recent arrivals in a story vastly older than ourselves. And so at last we return to where we began, to this moment, to this room, to this present where you rest. The ancient world recedes like a tide pulling back from shore, leaving only impressions, memories of what was and what we've discovered. Let the weight of those 160 million years settle gently over you like the most comfortable blanket imaginable. Not heavy or oppressive, but soothing, putting everything into perspective. Breathe slowly. Feel your body sinking deeper into rest with each exhalation. The dinosaurs lived their lives under the same sun that will rise tomorrow morning. Though so much has changed in between, they felt warmth and cold, hunger and satiation, danger and safety. They raised young, formed social bonds, and navigated complex worlds. And when their time ended, life continued, as it always does, finding new forms and new paths forward. You've travelled an immense distance tonight, from the scorching Triassic deserts to the lush Jurassic forests, from the flower-filled Cretaceous meadows to the cold aftermath of extinction. You've met giants and tiny hunters, herbivores and predators, creatures that flew and swam and strode across ancient ground. Now let them rest. Let the images fade softly into pleasant dreams. Let the roar of predators diminish to gentle whispers. Let the thunder of approaching herds become the quiet rhythm of your own heartbeat, steady and calm. Let ancient sunlight dim to comfortable darkness where rest comes easily. The dinosaurs lived for 160 million years. They will live forever in stone and memory, in the birds that sing each dawn, and in the wonder they inspire in hearts young and old. Their story is part of Earth's story, and Earth's story is part of the cosmic story. Stars and planets, time and change, life emerging, flourishing, transforming, and continuing always. Sleep well knowing you've touched deep time tonight, connected across the ages with creatures that once lived as fully and completely as you do now. May your dreams be peaceful, your rest complete, and may you wake refreshed, carrying a piece of that ancient world forward into tomorrow. The giants have settled down for the night. Join them in rest. The story will still be there in the morning, waiting patiently as it has for millions of years. For now, simply breathe, simply rest, simply be. Good night, traveller through time. Sleep well.